Look up at the night sky on a clear, dark evening. You see countless stars, distant galaxies, and the vast, beautiful emptiness of space. It's an incredible sight, but it's also a cosmic illusion. What you're actually seeing, what our most powerful telescopes can detect, is less than 5% of the universe. The rest, the overwhelming majority of everything that exists, is completely invisible to us. It's a shadow universe made of two mysterious and powerful forces that we call dark matter and dark energy. These two components are the greatest unsolved puzzles in all of modern science, the invisible architect shaping the cosmos on the grandest scale, and for nearly a century they have utterly baffled our brightest minds. This isn't just a small gap in our knowledge, it's a chasm. We live in a universe where we understand the recipe for a star, but we don't know what 95% of the universe is actually made of. This is the story of our quest to understand that profound mystery. It's a journey to the very edge of known physics, where the rules seem to break down and the universe reveals how truly strange it can be. Dark matter is the unseen skeleton, the gravitational glue that holds galaxies together and weaves the cosmic web. Without it, our Milky Way would simply fly apart. Yet we can't see it, touch it, or directly detect it with any instrument we've ever built. It whispers to us only through its immense gravitational pull. And then there's dark energy, an even more bizarre and potent phenomenon. It's the mysterious force causing the expansion of the universe to accelerate, pushing galaxies apart at an ever-increasing rate, driving the cosmos toward a cold, dark, and lonely future. Together, these two enigmas tell us that our reality is far stranger and more wonderful than we ever imagined. So, how do we begin to solve a puzzle this immense? We start by asking the right questions. In this video, we're going to embark on a thrilling exploration of 30 of the most intriguing, mind-bending mysteries surrounding dark matter and dark energy. We'll look at the ghostly evidence for their existence, the bizarre particles that might make up the dark universe, and the revolutionary experiments hunting for them right now. We'll dive into theories that sound like science fiction and confront possibilities that challenge our very understanding of reality. This is an invitation to pull back the curtain on the cosmos and explore the deepest secrets it has been keeping. So get ready, because we are about to journey into the dark heart of the universe, and what we find there will forever change how you see the night sky. Our story begins not in the depths of space, but right here in our own cosmic backyard, with a puzzle so fundamental it forced astronomers to invent an entirely new kind of reality. Consider a simple, spinning object like a child's merry-go-round. The horses on the outside have to move much faster than those near the center to complete a full circle at the same time. For decades, we assumed galaxies worked the same way. We thought the stars closer to a galaxy's center, bound tightly by the collective gravity of the galactic core, would orbit at tremendous speeds, while the stars out in the sparse, distant suburbs would move much more slowly, just like the outer planets in our solar system crawl along in their stately orbits around the sun. This elegant assumption was completely shattered by the meticulous work of astronomer Vera Rubin in the 1970s. By carefully measuring the rotation speeds of stars and gas clouds at different distances from the centers of spiral galaxies, she and her colleague Kent Ford discovered something astonishing. The stars out on the far edges of the galaxy were not moving slowly at all. They were whipping around just as fast as the stars near the brightly lit center. This was the equivalent of finding all the horses on that merry-go-round, even the ones way out on the rim, spinning at the exact same breakneck speed. According to the laws of gravity as we understand them, a galaxy spinning this fast should not be able to hold itself together. The tremendous centrifugal force should have long ago flung all those outer stars off into the void, tearing the galaxy into a scattered cloud of cosmic debris. The only logical conclusion was that there had to be something else there, something we couldn't see. This invisible substance had to be providing an immense amount of extra gravity, creating a powerful gravitational well deep enough to keep those speeding stars from flying away. Think of it like this: if you only saw the lights of a city at night, you might assume it's just a collection of buildings. But if you then saw cars racing through the streets at impossible speeds without crashing, you'd be forced to conclude that the city is actually built on the slopes of a massive, invisible mountain, whose gravity is what's keeping everything anchored in place. That mountain is dark matter. The sheer amount of this missing mass is staggering. To explain the rotation curves Rubin observed, this dark matter must outweigh all the visible stars, planets, and cosmic gas in a galaxy by a factor of 5 to 1. For every single particle of the ordinary matter that makes up you, me, and every star we can see, there must be at least 5 particles of this mysterious, invisible substance holding it all together. This was the first compelling, direct evidence that we are living in a universe dominated by a reality we cannot perceive, a ghostly framework without which the cosmic structures we take for granted simply could not exist. But the story of dark matter doesn't end with individual galaxies holding themselves together. Its true power is revealed on the largest canvas imaginable, where it acts as the master architect for the entire visible universe. If you could pull back and view the cosmos on the grandest scale, you wouldn't see galaxies scattered randomly like stars in the night sky. Instead, you would witness an immense, delicate structure, a cosmic web of staggering proportions. This web consists of vast, thread-like filaments of galaxies stretching for hundreds of millions of light years, intersecting at dense nodes where huge galaxy clusters reside, all separated by enormous, empty voids of near-total nothingness. This is the large-scale structure of the universe, and the stunning fact is that this entire framework is built not from the galaxies we see, but from the dark matter we cannot. This invisible dark architecture is the essential scaffolding upon which everything luminous is hung. We know this because our most sophisticated computer simulations of universal evolution can only produce the cosmos we see when they include a dominant amount of dark matter. When scientists program the laws of physics and the initial conditions of the Big Bang into a supercomputer and let it run, simulating billions of years of cosmic expansion and growth, a universe made only of ordinary matter remains a formless, thin soup. Stars and galaxies simply don't form, but when they add in dark matter, something magical happens, because dark matter doesn't interact with light or regular matter in any way other than gravity. It isn't pushed around by the intense radiation pressure of the early universe. This allows it to start clumping together first, collapsing under its own gravity into a sprawling network of filaments and halos. These halos act as gravitational traps. Once they form, their immense pull begins to draw in the surrounding ordinary matter, the hydrogen and helium gas, which then cools, condenses, and eventually ignites into the first stars and galaxies. The glittering cities of the cosmos only formed because the dark matter laid down the roads and built the foundations first. The process of mapping this invisible skeleton is one of the most brilliant detective stories in modern astronomy, and the key tool is a phenomenon predicted by Einstein's theory of general relativity called gravitational lensing. The principle is that mass warps the fabric of space-time. A tremendous concentration of mass, like a huge halo of dark matter, acts like a lens, bending the path of light from galaxies that lie far behind it. When astronomers look at a massive galaxy cluster, they sometimes see the background galaxies stretched and distorted into faint, smeared arcs and multiple images. It's like looking through the bottom of a wine glass at a distant light, seeing it warped and magnified. By meticulously measuring these subtle distortions in the shapes of millions of distant galaxies, astronomers can essentially trace the distribution of the invisible mass that is causing the warping. This technique allows us to create maps of the dark matter web directly, revealing the ghostly filaments and the cavernous voids in breathtaking detail. We are literally drawing a picture of the invisible, using the distorted light from the far universe as our pen. This confirms that the majestic cosmic web we observe is truly just the outline, the glittering trace of something far more massive and mysterious holding it all up from the shadows. So we've mapped the cosmic scaffolding, we've seen its ghostly gravitational hand at work, but this brings us face to face with the most urgent and humbling question of all. What exactly is it? What is this invisible substance that makes up over 80% of all the matter in the universe, yet has managed to evade every direct attempt to capture or observe it? The honest answer is we still don't know, but that hasn't stopped physicists from devising a fascinating menagerie of theoretical particles that could solve the puzzle. For decades, the leading candidate has been a class of particles known as WIMP, an acronym that stands for Weakly Interacting Massive Particles. The name itself tells you almost everything you need to know. They're hypothesized to be massive, meaning they carry significant weight, perhaps dozens or even hundreds of times the mass of a proton. More crucially, they interact only through the weak nuclear force and gravity, completely ignoring the electromagnetic force. This means they don't absorb, reflect, or emit light, rendering them perfectly, utterly dark. The elegance of the WIMP hypothesis, what made it so compelling for so long, was a concept known as the WIMP miracle. Calculations from the early universe showed that if a stable particle with these specific properties did exist, the sheer number of them created in the hot forge of the Big Bang would naturally freeze out to leave behind almost exactly the density of dark matter we observe today. It was a breathtakingly beautiful fit, a solution that seemed to tie particle physics directly to the cosmology of the entire cosmos. This theoretical promise launched a global hunt of epic proportions. Deep underground, in abandoned mines and beneath mountains, physicists built incredibly sensitive detectors to try and catch a WIMP in the act. The idea is that our entire solar system is moving through a vast halo of dark matter that permeates our galaxy. So even as you sit there, billions of these invisible particles should be streaming through your body and through the Earth every second. To find one, you need to go deep underground to shield the experiment from the constant rain of cosmic rays that would drown out the signal. There, in the profound quiet and cold, scientists wait for the telltale, once in a blue moon vibration, the infinitesimal recoil of a single atomic nucleus if it were ever struck by a passing WIMP. For years, these experiments have been growing larger and more sensitive, pushing the boundaries of detection. Yet, despite this monumental effort, the result has been a profound and growing silence. Not a single confirmed WIMP signal has been found. The parameter space where these particles could be hiding has been shrinking year after year, forcing the physics community to seriously consider that the answer might be something else entirely. And so, the search has broadened into a much wider and more exotic field of candidates. One compelling alternative is the axion. Where WIMP are imagined as heavy, lumbering giants, axions are theorized to be fantastically light and wispy, potentially billions of times lighter than an electron. They were originally proposed to solve a completely different, esoteric problem in particle physics concerning the strong nuclear force. But it was soon realized that if they exist, they could also be produced in vast numbers in the early universe and would collectively behave as a kind of coherent, wave-like fluid of cold dark matter. Detecting an axion is a completely different kind of challenge. Instead of looking for a nuclear recoil, experiments use powerful magnetic fields to try and convert these ghostly particles into faint microwave photons, listening for a specific, subtle tone rising from the quantum noise. Then there are proposals like sterile neutrinos. We know neutrinos exist, they're light, neutral particles that barely interact with anything, but the known types are all too fast and light to be the main dark matter. A sterile neutrino would be a heavier, right-handed cousin that mixes with ordinary neutrinos and could slowly decay, producing faint X-ray signals that astronomers are now searching for in galaxy clusters. And we can't forget the possibility that dark matter isn't a new particle at all, but rather a population of ancient primordial black holes. These wouldn't be the black holes formed from dead stars, but ones forged in the extreme densities of the universe's first moments, ranging in size from asteroids to planets. The hunt for these involves looking for the rare moments when one passes in front of a distant star, its gravity briefly bending the starlight and causing a telltale microlensing event. This incredible diversity of ideas, from heavy WIMP to wispy axions to ancient black holes, is both a testament to human ingenuity and a stark reminder of our profound ignorance. We have overwhelming evidence that dark matter is out there, shaping the cosmos on the grandest scales, yet after decades of increasingly sophisticated searches, its fundamental identity remains one of the most significant open questions in all of science. The mystery has only deepened. Is it one single type of particle or a whole hidden sector of dark particles interacting through their own dark forces? The continued silence in our detectors is itself a powerful piece of data, telling us that the universe is stranger and more subtle than our most elegant theories predicted, and that the final answer, when it comes, will likely revolutionize our understanding of reality itself. This brings us directly to one of the most dramatic and perplexing chapters in the entire saga, the Great Silence from Earth. For decades, the logical next step seemed clear. If our galaxy is indeed swimming in a vast ocean of dark matter particles, then we should be able to reach out and catch one. This conviction spurred a monumental, global effort to build the most sensitive, quietest particle detectors in human history. The strategy is as ingenious as it is challenging. To escape the constant bombardment of cosmic rays and other distracting background radiation from space, these experiments are built in places of profound stillness, deep within abandoned gold mines in South Dakota, under mountains in Italy, or at the bottom of specialized research facilities. They are technological cathedrals built in the dark, dedicated to listening for a whisper from the void. The most famous of these endeavors are the liquid xenon experiments like Lux Zeppelin and Xeno NNT. Imagine a colossal, multi-layered thermos flask, but instead of coffee, it's filled with several tons of ultra-pure liquid xenon, chilled to extremely low temperatures. At the top and bottom of this dark, pristine tank are arrays of incredibly sensitive light sensors. The principle is to wait for a dark matter particle, a WIMP, to drift through the tank and, on a very rare occasion, bump into the nucleus of a xenon atom. That tiny collision would produce two flashes of light, a quick initial spark when the particle hits, and a second, brighter flash when electrons liberated by the collision are drawn to the top of the chamber. By analyzing the timing, size, and location of these twin flashes, scientists can, in theory, distinguish a genuine dark matter interaction from the mundane chatter of residual radioactivity. These experiments represent the pinnacle of human precision, capable of detecting energy depositions so minuscule they are almost beyond comprehension. They are, in every sense, the quietest rooms in the universe, listening for a guest that has been invited for nearly half a century. Yet, after years of operation and continuous refinement, the result has been a profound and unsettling silence. The detectors work flawlessly, confirming their sensitivity by seeing known background events, but the specific, unique signal of a dark matter particle remains conspicuously absent. This growing null result has cast a long shadow over what was once the most cherished theoretical idea in the field, the WIMP miracle. This wasn't just a hopeful guess. It was a breathtaking mathematical coincidence that suggested particles with the right mass and weak scale interactions would naturally be produced in the exact abundance we now attribute to dark matter during the hot Big Bang. It was a solution that seemed to elegantly connect the world of the very small, particle physics, with the world of the very large, cosmology. The fact that we haven't found them where this miracle predicted they should be has created a deep and growing tension between theory and experiment. The parameter space, the range of possible masses and interaction strengths where WIMP could live, has been systematically chipped away year after year, like a map slowly being redrawn to show ever more territory as empty ocean. This relentless silence is forcing a profound and necessary rethink. One possibility is that we were simply too optimistic about how easy dark matter would be to find. Perhaps these particles interact even more weakly than we imagined, not just through the weak nuclear force, but through some new, far feebler force we have not yet discovered. In this scenario, our current detectors, as sensitive as they are still like trying to hear a pin drop in a hurricane. We need to build even bigger, even quieter experiments to have a chance. Another, more radical possibility is that we have been hunting for the wrong quarry all along. The WIMP, for all its theoretical elegance, might just be one of many ideas in a much richer and stranger zoo of dark matter candidates. Our fixation on it may have been a case of cosmic confirmation bias, where we fell in love with the most beautiful solution, only for the universe to reveal itself as more practical or more bizarre. The failure to detect WIMP directly is not a story of scientific failure, but one of necessary course correction. It is the universe telling us, in no uncertain terms, that the true nature of the dark sector is more elusive and more inventive than we had dared to dream. As we push further into the puzzle of dark matter, we encounter a mystery that strikes at the very heart of our models for how the universe is structured. This is the curious case of the missing satellites. When cosmologists run their most powerful supercomputer simulations of cosmic evolution, they feed in all the ingredients we think we understand: the laws of physics, the initial conditions of the Big Bang, and a dominant amount of cold dark matter. These virtual universes evolve over billions of simulated years, and they produce a result that is both beautiful and, in one key aspect, deeply confusing. The simulations show that large galaxies, like our own Milky Way, should not be solitary islands. They ought to be surrounded by a vast swarm of hundreds, even thousands, of smaller dark matter clumps, each one a potential host for a tiny, dim dwarf galaxy. This prediction makes perfect sense from a dark matter perspective. The theory suggests that structure forms from the bottom up, with small halos forming first and then merging to build larger galaxies. Many of these small, primordial halos should have survived intact, becoming the galactic equivalents of moons orbiting a planet. But when astronomers look up at the sky, the reality tells a different story. We don't see hundreds of satellites around the Milky Way. We've only confidently identified about 6 dozen. For a long time, the discrepancy was staggering. The simulations were predicting an order of magnitude more satellites than we could find. It was as if our theoretical blueprint for the cosmos had meticulously drawn every single small outbuilding and toolshed around a mansion. But when we looked at the actual property, we only saw the main house and a few nearby garages. Where was everything else? This missing satellites problem became a serious challenge, creating a tension between the stunning success of dark matter on large scales and its apparent failure on the smaller scales of individual galactic neighborhoods. It forced scientists to ask a difficult question: was there a flaw in the dark matter paradigm itself, or were we simply not seeing the full picture? One of the most promising solutions leans on the idea that we have been, quite literally, looking in the dark. The vast majority of these predicted satellite halos could indeed be out there, but they are so utterly faint that our telescopes have simply missed them. The key factor here is the difference between a dark matter halo and a visible galaxy. A halo is just a gravitational pit of dark matter. For it to become a galaxy we can see, it needs to pull in ordinary gas, mostly hydrogen, which must then cool, condense, and eventually ignite into stars. It's entirely possible that a huge number of these small halos fail to attract or retain enough gas to form a significant number of stars. They would be what astronomers call dark galaxies. immense balls of dark matter containing perhaps only a handful of stars or even no stars at all, rendering them virtually invisible to our surveys. Recent, more sensitive astronomical projects have started to chip away at the problem, discovering a new population of incredibly faint and diffuse dwarf satellites that were previously hidden in the glare of the night sky. Each new discovery helps bridge the gap between prediction and observation, suggesting that many of the missing satellites aren't truly missing. They've just been hiding in plain sight, waiting for our technology to become good enough to spot them. But there's another compelling piece to this puzzle, one that involves the raw, violent power of star formation itself. Even if a small dark matter halo does manage to pull in some gas and begin forming stars, the story doesn't necessarily end with a thriving dwarf galaxy. In these small, gravitationally fragile systems, the very first generations of stars can be a death sentence. Massive stars live fast and die young, exploding as supernova with titanic force. In a giant galaxy like the Milky Way, the immense gravity holds everything together, and such explosions are just energetic events within a vast system. But in a tiny dwarf galaxy, the collective blast from multiple supernovae can generate powerful winds that blow all of the remaining gas clean out of the halo. This process, known as supernova feedback, effectively shuts down all future star formation. The galaxy's growth is stunted in its infancy. What's left is a dark matter halo that used to have a bit of gas and a few stars, but is now a dark, dormant relic, its stellar population frozen in time. This idea provides a dual solution. It explains why we see fewer bright satellites than predicted, and it also accounts for why the dwarf galaxies we do see are generally so faint and devoid of young stars. Their potential was quashed by the very first fires that lit up within them. This intricate interplay between dark matter's gravitational pull and the astrophysical processes of stellar feedback is a frontier of modern cosmology. It shows us that the universe is not just a simple consequence of gravity, but a complex dance between the dark, invisible scaffolding and the luminous, often violent behavior of ordinary matter. The missing satellites problem is no longer seen as a fatal flaw for dark matter, but rather as a crucial testing ground. It pushes our simulations to become more sophisticated, forcing them to incorporate the messy details of gas physics, star formation, and explosive feedback. Solving this mystery means learning not just about the dark side of the universe, but also about the dramatic life cycles of the smallest and most numerous galaxies, the tiny, flickering candles that illuminate the vast, dark halls of the cosmic web. As we move from the challenge of counting dwarf galaxies to looking inside them, we encounter another perplexing issue that strikes right at the mathematical heart of the dark matter hypothesis. This is the cuspy halo problem, a conflict between what our most trusted computer models predict and what we actually observe when we measure the gravitational pull within real galaxies. According to the standard cold dark matter model, which has been spectacularly successful on cosmic scales, the halos of dark matter surrounding galaxies should have a very specific internal structure. Supercomputer simulations consistently show halos with a cuspy density profile. This means the concentration of dark matter should rise sharply and steeply as you approach the very center of the galaxy, creating a pronounced density cusp. Imagine a vast, invisible mountain where the slope becomes almost vertical as you near the peak. The gravitational pull in that central region should be incredibly intense. However, when astronomers study the motions of stars and gas within many dwarf galaxies and other low-surface brightness galaxies, the very systems dominated by dark matter, they find a very different reality. Instead of that predicted sharp cusp, the data overwhelmingly suggests the existence of a core that is much flatter. It appears that in the central regions of these galaxies, the density of dark matter remains relatively constant, as if the very peak of that invisible mountain had been sheared off and replaced with a gentle, rolling plateau. The gravitational pull in the center is significantly weaker than the simulations say it should be. This isn't just a minor discrepancy, it's a fundamental tension between a key prediction of our leading cosmological model and direct observational evidence. It forces us to ask a difficult question. Is there something wrong with our simulations, with our understanding of dark matter itself? Or are we failing to account for the transformative power of the ordinary matter we can see? One compelling line of investigation suggests that the solution lies not in the dark sector, but in the volatile behavior of stars and gas. This is the theory of baryonic feedback. Baryons is the collective term for the ordinary matter that makes up stars, planets, and us. While dark matter provides the gravitational foundation, baryonic matter is far from a passive passenger. In the dense centers of galaxies, cycles of intense star formation can create tremendous astrophysical violence. When massive stars are born, they flood their surroundings with intense radiation and powerful stellar winds. When they die, they do so in spectacular supernova explosions, detonating with the force of millions of nuclear bombs. All this energy doesn't just light up the galaxy. It violently heats up and churns the surrounding gas, pushing it outwards in vast, turbulent outflows. This constant churning and pumping of energy from the baryons can have a profound effect on the distribution of the dark matter itself. Think of it like stirring a thick soup with a giant spoon. The swirling motion redistributes the ingredients. In gravitational terms, as large clumps of gas are violently pushed around, the changing gravitational potential acts as a kind of mixer, transferring energy out to the dark matter particles and causing them to migrate slowly away from the center. Over billions of years, this relentless astrophysical feedback could gradually erase the sharp central cusp, smoothing it out into the observed flat core. In this scenario, the cuspy halo problem isn't a failure of dark matter theory, but rather a sign that our simulations need to become even more sophisticated. We need virtual universes that don't just model the gravity of dark matter, but also capture the incredibly complex, high-energy physics of star formation and stellar death. When these detailed feedback mechanisms are included in the most advanced simulations, they are indeed beginning to show that cores can be formed, reconciling the model with the observations. Yet another school of thought proposes a more radical fix, one that requires altering the fundamental nature of dark matter. What if dark matter isn't entirely collisionless as we've always assumed? The standard model posits that dark matter particles pass right through each other and through ordinary matter as if they were ghosts. But what if they possess just a tiny ability to interact with each other through some new, unknown force? This concept is known as self-interacting dark matter. If dark matter particles could scatter off one another, similar to billiard balls, this would provide a powerful mechanism to smooth out central cusps. In the dense core of a galaxy, where particle encounters would be most frequent, this self-interaction would transfer energy from the faster-moving particles to the slower ones, effectively creating a kind of dark matter pressure that prevents the extreme density spike from forming. The halo would naturally relax into a profile with a flatter core, much like a gas cloud settles into a state of equilibrium. This is an elegant solution that directly modifies the dark matter recipe, and it remains a viable and active area of theoretical research. The existence of this debate between complex baryonic feedback and a simple change to dark matter's properties is a perfect example of the scientific process at work. We are confronted with a clear anomaly, a crack in our theoretical edifice. Do we fill that crack by adding more intricate details to our model of the known universe, the bustling world of stars and gas? Or do we take it as a clue that the unknown universe, the dark sector itself, is more complex and interactive than we ever imagined? The cuspy halo problem, once a major point of contention, is now a rich testing ground. It pushes our computational models to new heights of realism and challenges our particle physics theories to explore more exotic possibilities. Solving this mystery will require us to look deeper into the faint hearts of dwarf galaxies, refining our observations, and to run ever more comprehensive simulations that bridge the vast gap between the ghostly pull of dark matter and the brilliant, explosive fury of the stars it hosts. Just when we thought we had a handle on the grand narrative of the cosmos, a story that began with a big bang and would end with either a fiery crunch or a slow, cold fade, the universe delivered a plot twist so profound it completely rewrote the final chapters. For much of the 20th century, astronomers were engaged in a monumental quest to measure the universe's deceleration. The logic was seemingly unassailable. After the initial violence of the Big Bang, the mutual gravitational attraction of all the matter in the cosmos, every galaxy, every star, every particle of dark matter, must be acting like a cosmic brake, relentlessly pulling on the fabric of space and slowing down the expansion. The central scientific question was not if the expansion was slowing, but by how much. Would there be enough matter to eventually halt the expansion and reverse it in a big crunch, or just enough to slow it forever toward a gradual stop? Two rival teams of scientists set out to answer this question by using the most powerful cosmic mileposts they could find, a specific type of stellar explosion known as a Type I, a supernova. These are not just any exploding stars, they are thermonuclear bombs of astonishing consistency. They occur when a white dwarf star in a binary system siphons off too much material from its companion, pushing it over a critical mass threshold and triggering a runaway fusion reaction that always releases the same peak brightness. Because of this uniform brightness, astronomers can use them as standard candles. By measuring how bright these supernovae appear from Earth, they can calculate with remarkable precision exactly how far away they are. Furthermore, by analyzing the redshift of their light, how much it has been stretched as the universe expands, they can determine how much the universe has stretched since the moment the star exploded. By comparing supernovae at different distances, and thus looking back to different epochs in cosmic history, the teams aim to trace the expansion rate of the universe over billions of years and finally measure the strength of gravity's cosmic drag. The results, announced independently by both teams in 1998, sent a shockwave through the world of physics that is still reverberating today. Instead of finding that the more distant, ancient supernova were closer than expected, which would have indicated a faster expansion in the past that had since slowed down, they discovered the exact opposite. The faraway supernova were significantly fainter than their models predicted. This meant they were actually farther away than anyone had calculated. There was only one possible, mind-bending conclusion. The expansion of the universe was not slowing down at all. In the more recent past, the universe had actually started expanding faster. The cosmos, it seemed, had stepped on the accelerator. This was the equivalent of tossing a ball into the air, expecting it to slow down and fall back to Earth, but instead watching it shoot away from you at an ever-increasing speed. The discovery was so bizarre and so counter to all expectations that the teams spent years checking and rechecking their data for errors, ruling out cosmic dust, evolutionary effects in the supernova, and every other conceivable alternative. The evidence was undeniable. This monumental finding demanded a radical explanation, and physicists were forced to resurrect a concept that Einstein had once proposed and then famously discarded as his greatest blunder. The force responsible for this accelerating expansion was given a name that reflects our profound ignorance of its nature: dark energy. What dark energy is remains one of the biggest mysteries in science, but we can describe what it does. It appears to be a property of empty space itself, a kind of latent energy inherent to the vacuum that exerts a negative pressure, causing space-time to stretch apart. Unlike gravity, which pulls things together, dark energy works as a repulsive force on cosmic scales, pushing galaxies away from one another. The most shocking implication is the sheer dominance of this mysterious component. When we add up the energy budget of the universe today, all the ordinary matter that makes up every planet, star, and galaxy accounts for a mere 5%. The dark matter that holds cosmic structures together makes up about 27%. The remaining 68%, the overwhelming majority of everything in existence, is dark energy. It is the prime driver of the cosmos's ultimate fate. This single discovery overturned decades of established cosmology and revealed a universe that is far stranger, more dynamic, and more mysterious than we had ever dared to imagine. So if dark energy is this mysterious force driving the cosmos apart, what could possibly be causing it? The most straightforward explanation, and the one that fits the current data best, takes us back to an idea first conceived by Albert Einstein himself. When he was developing his theory of general relativity, Einstein found that his equations describing the fabric of space-time naturally wanted the universe to be either expanding or contracting. But this was in 1915, and the prevailing scientific belief was that the universe was static and eternal. To force his equations into this static model, Einstein introduced a fudge factor, a term he called the cosmological constant. This constant represented a kind of inherent energy woven into the very vacuum of space, a repulsive force that could precisely balance the attractive pull of gravity, holding the universe in a steady state. Later, when Edwin Hubble discovered that the universe was indeed expanding, Einstein famously called the cosmological constant his greatest blunder, and it was discarded for decades. The irony, of course, is that with the discovery of the accelerating expansion in the late 1990s, the cosmological constant was resurrected in triumph. It turns out Einstein's blunder was actually a glimpse of a profound cosmic truth. The universe does have a constant energy density in its empty space. We just call it dark energy now. This concept of a cosmological constant leads us directly to one of the most mind-bending ideas in modern physics, vacuum energy. In our everyday experience, a vacuum is just empty space, a true void. But according to quantum field theory, the bedrock of our understanding of particles and forces, empty space is anything but empty. At the tiniest scales, the vacuum is a seething, bubbling foam of virtual particles. These are particle-antiparticle pairs that spontaneously pop into existence out of nothing, borrowing energy from the universe for an infinitesimally brief moment before annihilating each other and vanishing back into the void. This isn't just a mathematical quirk. We see the effects of this quantum frenzy in real, measurable phenomena, like the subtle shift in the energy levels of atoms, known as the Casimir effect. All this frantic activity endows every single cubic centimeter of what we call nothing with a certain energy density. This vacuum energy, according to the theory, should be exactly what the cosmological constant is, a constant, unchanging energy inherent to space itself that exerts a negative pressure, causing the cosmos to expand at an accelerating rate. It's an elegant and beautiful connection between the world of the quantum and the fate of the entire cosmos. Here, however, we run headlong into what is often called the most embarrassing problem in all of theoretical physics. If we can use the well-established rules of quantum field theory to calculate the expected value of this vacuum energy, we can compare that prediction to the actual, observed value of dark energy that we measure from the accelerating expansion of the universe. The result of this comparison is not just a little bit off. It is a discrepancy of such staggering magnitude that it is almost impossible to comprehend. The theoretical prediction for the vacuum energy is about 10 to the power of 120 times larger than the observed value. That's a 1 followed by 120 zeros. To put that number in perspective, it is a greater difference than the scale between the size of the entire observable universe and the size of a single subatomic particle. It is, by a colossal margin, the worst prediction in the entire history of science. This is the cosmological constant conundrum in its most acute form. Our two most powerful and successful theories, quantum mechanics for the very small and general relativity for the very large have come together to make a prediction that is catastrophically, undeniably wrong. This isn't just a minor mathematical inconvenience. It points to a fundamental gap in our understanding, a problem of fine-tuning that is so extreme it defies belief. For the universe to look the way it does with galaxies and life, the value of the cosmological constant has to be incredibly small, but not quite zero. If it were significantly larger, even by a tiny fraction, the repulsive force would have been so powerful in the early universe that it would have torn apart every incipient galaxy before it could even form. No stars, no planets know us. If it were negative, the universe might have collapsed back in on itself almost immediately after the Big Bang. The fact that we exist in a universe where this value is so exquisitely balanced on a knife's edge is what physicists call a fine-tuning problem. Why does the vacuum energy cancel out to almost, but not perfectly, zero, leaving behind just the minuscule remnant we call dark energy? It seems as though the fundamental constants of nature have been set with unbelievable precision to allow for a cosmos that can eventually support life. This realization leads some physicists to consider the anthropic principle, the idea that the universe must have the properties it does because we are here to observe it. In a hypothetical multiverse where countless universes have different physical constants, we simply find ourselves in one of the rare, hospitable ones where the numbers just happen to work out. For others, the vacuum catastrophe is a clear signal that we are missing a crucial piece of the puzzle. Perhaps our understanding of quantum field theory is incomplete when applied to the vacuum on cosmic scales. Maybe there is a hidden symmetry or a new physical principle that forces the vacuum energy to be exactly zero, and what we are measuring as dark energy is something else entirely, a dynamic field that changes over time, similar to the inflationary field that propelled the universe's exponential expansion in its first fleeting moments. The cosmological constant conundrum is more than just a mystery, it is a direct challenge. It tells us that a simple, elegant marriage of general relativity and quantum mechanics is not enough. Unifying these two pillars of physics into a theory of quantum gravity, perhaps through string theory or loop quantum gravity, is the holy grail of modern physics, and solving the cosmological constant problem is the most pressing reason to find it. The fate of the universe, it seems, is tied to the deepest and most unresolved questions at the foundation of reality itself. But if the cosmological constant is such a problematic answer, could it be that we're asking the wrong question? What if dark energy isn't a fixed feature of empty space at all, but something far more dynamic and strange? This brings us to a compelling and mysterious alternative. The idea that dark energy is not constant but evolves. The leading candidate for this theory is known as quintessence. In ancient philosophy, the quintessence was the fifth element, a pure and perfect substance that permeated the heavens. In modern cosmology, it represents a completely different kind of energy, a dynamic field that fills space, but one whose strength and density can change over the vast expanse of cosmic history. Unlike the rigid, unchanging cosmological constant, quintessence can vary, meaning the repulsive force driving the universe apart could have been different in the past and could change again in the future. This isn't just a minor tweak to the model, it's a fundamental reimagining of the dominant component of our universe, transforming it from a static backdrop into an active, evolving player in the cosmic story. The key to testing this profound idea lies in meticulously reconstructing the universe's expansion history. Think of it like trying to understand the performance of a car's engine by studying its speed over a long journey. The discovery of acceleration in 1998 was like noticing that the car is now going faster. But was it always accelerating at this exact rate? Did it speed up gradually or in fits and starts? To distinguish between a simple cosmological constant and a dynamic field like quintessence, we need to measure the expansion rate at many different points in the past, tracing how the strength of dark energy has changed over billions of years. This is an incredibly delicate task, and it's the primary mission of a new generation of cosmic observatories, the Nancy Grace Roman Space Telescope, set to launch in the next few years, and the Vera Rubin Observatory, currently under construction in Chile, are not just new telescopes, they are time machines designed for forensic cosmology. They will scan enormous swaths of the sky, discovering and measuring billions of galaxies and mapping the distribution of dark matter through gravitational lensing with unprecedented precision. By combining these vast datasets, they will create a super-fine-grained movie of the universe's expansion, allowing us to see if the push of dark energy has remained a steady hand on the cosmic accelerator, or if its foot has been pressing down harder, or perhaps even easing up as time has gone by. The implications of finding a dynamic dark energy are nothing short of staggering, completely rewriting the possible endings for our cosmos. If dark energy is truly a constant cosmological constant, the future is one of gradual but relentless isolation. Galaxies outside our local group will continue to recede until their light can no longer reach us, and the universe will cool and darken over trillions of years in what is often called a heat death. But if dark energy is a form of quintessence that grows stronger with time, the outcome could be infinitely more violent and dramatic. This scenario leads to a hypothetical finale known as the Big Rip. In this terrifying endgame, the repulsive force of dark energy wouldn't just push galaxies apart. It would eventually overcome every force that holds things together. First, the gravitational bonds between galaxy clusters would be severed. Then, as the acceleration becomes more intense, individual galaxies would be torn asunder. Later, the gravitational glue holding stars within galaxies would fail. As the end approaches, the force would rip planets from their stars and then overcome the forces holding individual planets and stars together. In the final, fleeting moments, the crushing force would exceed the nuclear forces that bind atoms themselves, shredding every molecule, every atom, and every nucleus into a diffuse, disconnected cloud of fundamental particles. The entire fabric of the universe as we know it would be violently dissolved in a final, instantaneous catastrophe. The quest to determine the true nature of dark energy, whether it is a steady constant or a dynamic field, is perhaps the most important question in all of cosmology today. The answer will not only tell us what the universe is made of, but it will also dictate its ultimate fate. Are we headed for a long, quiet fade or a sudden, violent end? The tools to answer this are now being built, and within the next decade or two, the data they provide could reveal whether the force that dominates our universe is a simple, unchanging fixture of empty space, or a mysterious, evolving entity that holds the power to rewrite the final chapter of reality itself. Just when we thought we had a firm grasp on the universe's expansion history, a new and deeply puzzling inconsistency has emerged, one that threatens to unravel our most carefully constructed cosmological models. This is the Hubble tension, a stubborn and growing disagreement over one of the most fundamental numbers in all of cosmology, the Hubble constant, which measures the current rate of the universe's expansion. For years, we assumed that by measuring this number in different ways, we would eventually converge on a single, precise value. Instead, the opposite has happened. As our measurement techniques have become more and more sophisticated, the gap between the two primary methods has only widened, creating a rift that now stands as one of the most significant unsolved problems in modern science. The conflict arises from two fundamentally different approaches to measuring the expansion rate. The first method looks back to the very infancy of the universe, using the afterglow of the Big Bang itself, the cosmic microwave background. Satellite missions like Planck have mapped this relic radiation with exquisite detail, capturing a snapshot of the universe when it was just 380,000 years old. By feeding this pristine early universe data into our standard model of cosmology, known as lambda cold dark matter, scientists can run the cosmic film forward in time. The model, which includes precise amounts of dark matter and dark energy, predicts exactly how fast the universe should be expanding today. This method yields a very robust and consistent value for the Hubble constant. The second method takes a completely different path, focusing on the local universe, the cosmic neighborhood we can observe today. This is classic cosmic distance ladder work. Astronomers use incredibly reliable stars called Cepheid variables as their first rung. These stars pulsate at a rate that is directly tied to their true intrinsic brightness. By measuring their pulsation period from a nearby galaxy, astronomers can determine their real brightness, and then by comparing that to how dim they appear from Earth, they can calculate a precise distance. The next rung involves finding Type 1, a supernova in those same galaxies. Because these supernovae are also standard candles with a known peak brightness, their observed dimness gives us the distance to galaxies even farther away. By meticulously building this ladder and measuring the redshift of these distant galaxies, teams like the one led by Nobel laureate Adam Rees have arrived at a value for the current expansion rate. The problem is stark and undeniable. The local universe measurements consistently give a value for the Hubble constant that is significantly faster, by about 5 to 10%, than the value extrapolated from the early universe. At first, many scientists hoped this discrepancy was simply due to hidden systematic errors, tiny miscalibrations in our instruments, or unaccounted for dust. But after years of relentless checking, re-observing, and inventing new cross-checking techniques, the tension has not gone away, it has only solidified. The local measurement has become more precise, and the early universe measurement from Planck is one of the most successful and scrutinized datasets in history. This isn't a case of fuzzy data, it's a clear, persistent clash between two pillars of observational cosmology. The unsettling conclusion is that this might not be an error at all, but rather a thrilling clue. The Hubble tension could be the first hard evidence that our standard model of cosmology, the lambda cold dark matter model, is incomplete. Perhaps there is something about the universe's ingredients or the laws of physics themselves that we have not yet accounted for. The implications of this are profound, opening the door to a host of exotic possibilities. Maybe dark energy is not a simple cosmological constant, but is instead evolving, becoming stronger over time in a way that our models don't anticipate. This could explain why the universe is expanding faster now than our extrapolation from the early universe would predict. Alternatively, perhaps dark matter has properties we haven't considered. What if a small fraction of dark matter particles can decay or interact with radiation, subtly changing the way structures formed in the universe's adolescent years and altering the expansion history? Other, even more radical ideas suggest that the very nature of dark energy could be creating vast cosmic scale inhomogeneities, that our local region of the universe might not be entirely representative, like living in an unusually dense or sparse part of a much larger cosmic forest. Resolving the Hubble tension is now a primary driving force in astronomy, pushing the limits of our technology and imagination. New missions and telescopes like the James Webb Space Telescope and the Nancy Grace Roman Space Telescope are being tasked with tearing down the cosmic distance ladder and rebuilding it with unprecedented precision, scrutinizing every Cepheid variable and every supernova for any possible source of error. At the same time, future observatories will map the cosmic microwave background with even finer detail, searching for any subtle wrinkles that might hint at new physics. This isn't just an academic debate over a number, it's a fundamental test of our cosmic story. The Hubble tension is a cosmic warning light on the dashboard of our understanding, telling us that while we have learned an incredible amount about the universe, the most exciting discoveries, the ones that will force us to rewrite the textbooks, are likely still ahead. While the Hubble tension captures headlines for its direct challenge to the expansion rate, a second, more subtle anomaly has been quietly growing in the background, creating a parallel crisis in our understanding of cosmic structure itself. This mystery revolves around a fundamental question: just how clumpy is our universe? According to the supremely successful lambda cold dark matter model, the early universe was seeded with tiny quantum ripples that were then stretched to cosmic proportions by a brief period of ultra-fast expansion called inflation. These ripples are the primordial blueprints for all the structure we see today: the galaxies, the clusters, and the vast cosmic web. The precise pattern of these ripples is frozen in time within the cosmic microwave background, the afterglow of the Big Bang. When scientists analyze this pattern with observatories like the Planck satellite, they can derive a critical number that quantifies the universe's present-day lumpiness. This parameter is known as S8. Essentially, S8 tells us the amplitude of matter fluctuations on a scale of about 8 million light-years. A higher S8 value means a more clumpy universe with matter concentrated in dense knots and filaments. A lower value points to a smoother, more homogeneous distribution. The Planck measurement of the early universe gives us a very firm prediction for what S8 should be today. It paints a picture of a cosmos with a specific, rather pronounced level of structural complexity. But what happens when we stop looking at the ancient blueprint and instead go out and actually measure the finished cosmic building? This is where the tension, often called the S8 tension, emerges. To measure the actual clumpiness of the universe today, astronomers use a powerful technique we touched on earlier: weak gravitational lensing. By observing how the light from millions of distant galaxies is subtly distorted as it passes through the cosmic web of dark matter on its way to us, we can create a three-dimensional map of the distribution of all matter, both light and dark. These massive sky surveys, with names like the Dark Energy Survey and the Kilo Degree Survey, have now mapped the clumpiness of the cosmos with breathtaking precision. The results from these direct, modern measurements are consistent and startling. They find a value for S8 that is consistently lower than what the cosmic microwave background predicts. The universe, according to these lensing surveys, is smoother and less clumpy than the standard model says it should be. It's as if the ancient recipe called for a chunky, textured stew, but when we finally taste the dish today, it's noticeably smoother and more blended. This isn't a dramatic, orders of magnitude difference, but in the world of precision cosmology, where measurements are now made with percent-level accuracy, the discrepancy is significant and stubborn. It suggests that the growth of cosmic structures over the last 13 billion years did not proceed exactly as our models forecast. Something seems to have been subtly suppressing the formation of the largest clumps of matter in the universe. So, what could be causing this apparent smoothing of the cosmos? One compelling line of investigation points to the invisible protagonist of our story: dark matter. The standard model assumes dark matter is cold, meaning its particles move sluggishly, which allows it to clump together efficiently from the very earliest moments. But what if dark matter isn't perfectly cold? What if it has just a little bit of warmth? This idea, known as warm dark matter, proposes that dark matter particles are lighter and faster moving than in the traditional cold model. These faster moving particles would have been able to stream out of the very smallest density fluctuations in the early universe, effectively washing out some of the fine-scale structure. This would lead to a universe that forms fewer of the very smallest dwarf galaxies and, on a larger scale, could result in the overall lower clumpiness we observe today. Warm dark matter acts like a cosmic filter, smoothing out the initial ripples just enough to potentially explain why the universe appears less lumpy now than we expected. Another potential actor in this cosmic drama is a particle we already know exists, the neutrino. For a long time, the standard model of cosmology treated neutrinos as massless particles that flew through the universe at near light speed, contributing almost nothing to the gravitational buildup of structure. But we now know from particle physics experiments that neutrinos do have a tiny but non-zero mass. While each neutrino is unimaginably light, they are so unimaginably abundant that their collective gravitational influence might be more significant than we thought. These lightweight, fast-moving neutrinos are reluctant to collapse into gravitational wells. Instead, they tend to stream freely, and this behavior can also suppress the growth of the largest structures. If the combined mass of all three types of neutrinos is higher than our current best estimates, they could be providing enough of a smoothing effect to account for the lower S8 measurement. The universe's smoothness, in this case, wouldn't be a mystery of the dark sector, but a signature of these ethereal, known particles finally making their collective weight felt. The S8 tension, together with the Hubble tension, creates a powerful 1-2 punch against the simple, elegant version of our standard cosmological model. It suggests that the lambda cold dark matter model, for all its phenomenal success, might be an incomplete picture. The universe seems to be expanding a bit too quickly and is a bit too smooth for the model's liking. These aren't catastrophic failures, they are subtle whispers from the data, hints that the dark universe is more complex and nuanced than our simplest theories allow. They push us to consider more dynamic forms of dark energy or more interactive types of dark matter. They force us to re-evaluate the role of particles we thought we understood, like neutrinos. Most importantly, these tensions are not dead ends. They are the guiding lights for the next generation of astronomical surveys, upcoming projects like the Vera Rubin Observatory and the Euclid Space Telescope are designed specifically to measure weak lensing and cosmic structure with even greater precision, offering the best hope yet to determine whether this smoothness is a statistical fluke, a measurement quirk, or a genuine crack in our cosmic foundation, pointing the way toward a deeper and more complete theory of everything. Just as we were grappling with the large-scale smoothness of the cosmos, a very different kind of structural anomaly appeared much closer to home, one that strikes at the heart of how we think galaxies form. For decades, our best dark matter simulations didn't just predict a swarm of small satellite galaxies around giants like the Milky Way, they also predicted how these satellites should behave. In a universe dominated by cold dark matter, these small galaxies are expected to be ancient relics, the first clumps to form, which were then captured by the growing gravity of the larger galaxy. Crucially, they should arrive from all directions, like bees buzzing randomly around a hive. Their orbits should be a chaotic, isotropic jumble, resulting in a roughly spherical cloud of satellites orbiting the central galaxy. This expectation is a cornerstone of the hierarchical model of galaxy formation. But the real universe, once again, had a surprise in store when astronomers began to map the positions and movements of the Milky Way's satellite galaxies with greater precision. A startling pattern emerged. Instead of being scattered randomly across the sky, a significant number of them, including famous dwarfs like the Large and Small Magellanic Clouds, were found to be aligned along a single, vast and incredibly thin plane. This structure, now known as the vast polar structure, is like a giant rotating disk of dwarf galaxies nestled within the much larger spherical halo of our galaxy. Even more astonishing, when we look at our nearest large galactic neighbor, the Andromeda Galaxy, we see a very similar phenomenon. Andromeda's satellites are also arranged in a vast, thin, and co-rotating plane. This isn't just a quirky coincidence, it's a systematic feature that appears around both of the major galaxies in our local universe. Finding one such plane could be a fluke, but finding two suggests a fundamental challenge to our models. It's the equivalent of tossing a handful of marbles into the air and watching them not only land on a single dinner plate lying on the floor, but also start spinning together around its center. According to our standard simulations, this simply shouldn't happen with such regularity and thinness. This discovery creates a serious puzzle. If these satellite galaxies are truly the ancient, primordial building blocks predicted by the cold dark matter model, they should have been accreted over billions of years from all different angles. The gravitational tug of war and the sheer amount of time involved should have thoroughly mixed their orbits, erasing any such delicate pancake-like structure. The existence of these thin, rotating planes suggests that the satellites within them fell into the Milky Way's grasp much more recently and in a far more organized fashion. One of the most promising explanations for this involves a more chaotic and violent chapter in a galaxy's life, the process of group accretion. Imagine that the Milky Way didn't acquire its satellites one by one, but instead swallowed an entire group of dwarf galaxies in a single colossal bite. If a small galaxy group whose members were already orbiting a common center of mass was pulled into the Milky Way, it would naturally preserve some of that group's orbital coherence. The entire infalling group would tend to splatter along a preferred plane as it was torn apart by tidal forces, neatly depositing its member galaxies into the thin, rotating structure we observe today. This is a compelling narrative, but it comes with its own set of challenges. For this to work, the initial group of dwarfs would have to be quite large, and the accretion event would need to be relatively recent, on the order of a few billion years ago, for the plane not to have been disrupted by now. Furthermore, while this might explain the plane around the Milky Way, is it statistically likely for the same rare, massive group accretion event to have happened to both the Milky Way and Andromeda? Some simulations suggest it is possible, but it stretches the limits of probability, making astronomers wonder if there's a more fundamental mechanism at work that our models are missing. This leads to a more radical line of thought. What if the planes of satellites are not a problem with the accretion of dark matter, but with its very nature? A small but passionate group of researchers sees these structures as potential evidence for a competing model known as modified Newtonian dynamics, or MND. This theory proposes that there is no dark matter at all, and that the effects we attribute to it are actually caused by a modification of the laws of gravity at very low accelerations, such as those found in the outer reaches of galaxies. In certain MONDIAN models, when two large galaxies like the Milky Way and Andromeda have a close encounter, as they are destined to do in the future, the tremendous tidal forces can naturally warp and shape the distribution of smaller galaxies into these vast, co-rotating planes. From this perspective, the satellite planes are not a puzzling anomaly, but an expected outcome of a gravity that works differently than Einstein and Newton envisioned. For the majority of cosmologists who remain committed to the dark matter paradigm, the existence of these planes is a powerful call to action, not a death knell. It tells us that our simulations of galaxy formation, while brilliant on the largest scales, are still missing key pieces of physics. The models may need to better account for the dynamic interplay between the dark matter halo and the massive, rotating disk of ordinary matter at the galaxy's center. The gravitational influence of this central disk could potentially shepherd incoming satellites into a preferred plane over time. Or it could be that the dark matter halo itself is not a simple, fluffy sphere, but is significantly flattened, shaping the orbits of everything within it. The planes of satellite galaxies remain one of the most intriguing and hotly debated mysteries in near-field cosmology. They are a stark reminder that even in our own cosmic backyard, the universe is capable of organizing itself in ways that defy our simplest expectations, pushing us to develop a richer, more nuanced understanding of the dark forces that sculpt our galactic home. But perhaps the most direct challenge to our simulations comes not from what's missing, but from the very nature of the satellites we do find. This brings us to a mystery with a wonderfully ironic name, the too big to fail problem. It sounds like a financial term, and in a cosmic sense it is. our most sophisticated cold dark matter simulations predict that the Milky Way should be surrounded by a collection of subhalos, clumps of dark matter that never merged into the main galaxy. And among these, there should be a dozen or so that are truly colossal, the billionaires of the dark matter world. These are the most massive, most dense subhalos, with gravitational wells so deep and powerful that they should have had no trouble at all pulling in vast amounts of gas during the early universe. According to every rule of galaxy formation, these behemoths should have easily, almost inevitably, ignited with billions of stars, becoming the brightest and most spectacular satellite galaxies in our sky. Yet, when we look out at the actual satellite galaxies orbiting the Milky Way, the story is completely different. The brightest satellites we see, like the Large Magellanic Cloud and Sagittarius Dwarf, are not residing in these predicted supermassive halos. Instead, they appear to be living in much smaller, less massive dark matter clumps. The true giants, the subhalos that are too big to fail at forming stars, are nowhere to be seen. They seem to have failed spectacularly, remaining utterly dark and invisible. It's the cosmic equivalent of predicting that the most fertile, well-watered valleys on Earth would be home to sprawling megacities. But when you go to look, you find only small villages, while the great valleys themselves are mysteriously empty and barren. This isn't a minor accounting error. It's a fundamental mismatch between the raw gravitational potential our models predict and the luminous reality we observe. Why would the universe's most promising real estate, the sites with the strongest gravitational pull, somehow fail to build the glittering metropolises they were destined for? One compelling explanation brings us back to the dramatic power of star formation, but with a much more extreme twist. Imagine one of these massive, primordial dark matter halos in the early universe. It does its job perfectly, drawing in a huge reservoir of hydrogen and helium gas. This gas begins to cool and collapse, and the first generation of stars ignites. But in these incredibly dense environments, star formation might not just be vigorous, it could be catastrophically explosive. The first stars to form could be monstrously large, burning fiercely and dying in supernova of unimaginable power. In a halo with such a strong gravitational pull, you might think it could hold onto its gas, but the energy from these early blasts could be so intense that it doesn't just push the gas around. It effectively blows it all out in a single, titanic feedback event. The entire gaseous reservoir is heated to millions of degrees and ejected from the halo, permanently shutting down any future star formation. The dark matter halo, though massive and full of potential, is left a dark, starless ghost, a cosmic castle built with immense walls but with no one ever living inside. This quenching of star formation in the most massive subhalos could be the key to why they appear too big to fail, yet ultimately fail to shine. But there's another, even more intriguing possibility that goes right to the nature of dark matter itself. What if our assumption that dark matter is perfectly cold is just a little bit off? We've talked about warm dark matter as a solution to the missing satellites problem, but it could also be the key to the too big to fail problem. If dark matter particles have even a small amount of thermal motion, if they are warm instead of stone cold, this would have a profound effect on the very first structures to form. The warm dark matter particles would be moving fast enough to resist collapsing into the very smallest, densest clumps. This would naturally suppress the formation of the extremely high density peaks in the dark matter distribution. In this warmer universe, the most massive subhalos around a galaxy like the Milky Way would still exist, but they would be significantly fluffier and less centrally concentrated than in the cold dark matter simulations. Their gravitational wells would be shallower, making it much easier for supernova feedback to blow out the gas and prevent sustained star formation. The too big to fail problem, in this view, simply evaporates. The halos were never quite as big and dense as we thought in the first place, so their failure to form bright galaxies is no longer a mystery but an expected outcome. This ongoing debate between astrophysical feedback and the fundamental properties of dark matter is a beautiful example of how science grapples with a deep mystery. Are the darkest halos dark because of the violent lives and deaths of the first stars, a story written in the fire of ordinary matter, or is their darkness an intrinsic clue, a signature of the subtle warmth of the dark matter particle? The answer likely lies in a combination of both, and untangling this knot is a primary goal for the next generation of ultra-deep sky surveys. By studying the faintest, most pristine dwarf galaxies and measuring the precise distribution of dark matter within them, we hope to finally understand why the universe's greatest potential sometimes remains just that potential hidden in the dark, waiting for its story to be told. To truly grasp the profound influence of dark matter, we have to rewind the cosmic clock all the way back to the very beginning, to a time before the first stars flickered on, when the entire universe was a hot, dense, and nearly uniform soup of particles and energy. In these first fleeting moments, dark matter was already there, working behind the scenes. The critical point is that dark matter and ordinary matter, what scientists call baryonic matter, experienced the early universe in fundamentally different ways. For the first several 100,000 years, the cosmos was so incredibly hot and dense that light couldn't travel freely. Photons of light were constantly bouncing off and interacting with the charged particles of ordinary matter, the protons and electrons. This created a relentless radiation pressure, a powerful force that pushed against gravity, preventing the ordinary matter from easily clumping together. It was like trying to build a sandcastle in a stormy sea. The waves of radiation kept washing away any incipient structures. Dark matter, however, was completely immune to this chaos. Because it doesn't interact with light or electromagnetic forces at all, it was utterly oblivious to the intense radiation bath. This gave it a monumental head start. While ordinary matter was being buffeted and pushed around, dark matter could simply respond to gravity's quiet, persistent pull. It began to collapse into the tiny ripples of density that were imprinted on the cosmos by a period of hyper-expansion called inflation. These ripples, variations so minute they were once just quantum fluctuations, became the seeds for all future structure. Dark matter acted as the universe's premier architect, using its gravity to amplify these seeds, building an invisible skeleton of filaments and halos long before the first atom could form. This scaffolding, often called the cosmic web, provided the essential gravitational wells, the deep pits of potential energy, that would later trap the ordinary matter and allow it to cool, condense, and ultimately ignite into the very first stars and galaxies. Without this dark foundation, the ordinary matter would have remained a diffuse, formless fog, and the universe would be a dark and empty place, devoid of the brilliant structures we see today. We have a direct, frozen-in-time snapshot of this pivotal era, a baby picture of the universe that confirms dark matter's crucial role. This is the cosmic microwave background, the faint afterglow of the Big Bang that permeates all of space. It was released when the universe was just 380,000 years old, the moment it cooled enough for atoms to form and light to finally travel freely. This ancient light carries with it an imprint of the density and temperature variations of that infant cosmos. When we look at the incredibly detailed maps produced by satellites like Planck, we see a mottled pattern of hot and cold spots. These minute fluctuations are a direct record of the gravitational landscape at that time. The slightly denser, cooler spots correspond to regions where dark matter had already begun to clump, its gravitational pull creating pits that slightly redshifted the light trying to climb out of them. By analyzing the precise statistical properties of this pattern, cosmologists can perform a kind of cosmic archaeology. They can deduce that the total amount of matter in the universe is about 5 times greater than the amount of ordinary matter we can account for. The gravitational pull needed to create the cosmic structures we see forming in this baby picture simply couldn't have come from visible stuff alone. The cosmic microwave background is therefore one of the strongest and most direct pieces of evidence we have for the existence of dark matter, a fossilized whisper from the dawn of time telling us that the dark sector was already hard at work, laying the groundwork for everything to come. This brings us to one of the most profound and unresolved questions in all of cosmology. When and how was dark matter itself created? We know it had to be present in those very first moments to guide the formation of structure, but its own origin is shrouded in mystery. The leading theories point to an unbelievably early genesis within the first fraction of a second following the Big Bang. One compelling possibility is that dark matter particles were forged in the unimaginable heat of the universe's birth, a process known as thermal production. In this fiery cauldron, particle-antiparticle pairs of all kinds were constantly popping in and out of existence. As the universe expanded and cooled, these dark matter particles could have frozen out, ceasing to be created and annihilated, leaving behind a stable relic population that persists to this day. This is the elegant idea behind the WIMP miracle we discussed earlier, though the continued failure to detect WIMP directly has forced physicists to consider other, even more exotic birth scenarios. Another fascinating possibility is that dark matter is not a relic from a thermal bath, but was created through a non-thermal process. For instance, it could have been generated by the decay of other, even more mysterious fields that permeated the early cosmos. Imagine a cosmic field similar to the one thought to have driven inflation, oscillating and eventually collapsing, releasing its energy not as radiation, but by spraying a shower of stable, massive dark matter particles across the nascent universe. There's also the intriguing idea that dark matter could be connected to the mystery of why our universe is made of matter and not antimatter. The same processes that generated a tiny excess of matter over antimatter in the first instance might have also produced an asymmetry that led to the creation of dark matter. Or perhaps dark matter was produced during cosmic phase transitions, moments when the fundamental forces of nature separated from one another, much like water freezing into ice. These transitions could have created topological defects in the fabric of space-time cosmic strings or domain walls whose decay could have seeded the universe with dark matter. The true origin of dark matter remains one of the ultimate frontier questions, a puzzle that takes us right to the edge of known physics and forces us to confront what happened in the very first moments of reality, in a realm of energy and density so extreme that our current theories can only speculate. Unlocking this secret would not just tell us what dark matter is, but would open a window into the very birth of the cosmos itself. Since we can't seem to catch a single, solitary dark matter particle directly, maybe we're going about this the wrong way. Perhaps we don't need to find one at a time. Maybe we can detect them en masse by looking for the fallout from their cosmic interactions. This is the fascinating world of indirect detection, a strategy that turns the entire sky into one giant, natural dark matter detector. The core idea here is beautifully simple. If dark matter is indeed a particle, and if there are trillions upon trillions of these particles swarming through our galaxy, then occasionally they must run into each other. And if they can annihilate upon contact, just like a particle meeting its antiparticle, or if they can slowly decay over cosmic time, these processes should release a shower of secondary particles that we can see, things like gamma rays, X-rays, or cosmic rays like positrons and antiprotons. We wouldn't be seeing the dark matter itself, but the telltale burst of energy it leaves behind, the signature of its self-destruction. To find these faint signals, astronomers know exactly where to look, the places where dark matter is thought to be most densely packed. Imagine dark matter forming an immense invisible sphere around our galaxy, a halo that is most concentrated at its very center. The core of the Milky Way should therefore be a raging furnace of dark matter annihilation, a place where the density is so high that particles are constantly colliding. Dwarf spheroidal galaxies, those tiny, faint satellites of the Milky Way, are another prime hunting ground. While they contain very few stars, they are believed to be absolutely dominated by dark matter, making them incredibly clean targets. Unlike the galactic center, which is a messy, bustling place full of pulsars, supernova remnants, and other high-energy astrophysics, these dwarf galaxies are like quiet, dark laboratories in deep space. Any anomalous gamma rays we detect from them would be very difficult to explain without invoking dark matter. One of the most tantalizing and hotly debated hints from this search is known as the Galactic Center GVXS. For years, astronomers analyzing data from NASA's Fermi Gamma Ray Space Telescope noticed something peculiar. There was a faint, diffuse glow of gamma rays emanating from the region around the galactic center, with an energy of around 1 to 3 giga-electronvolts or GeV. This glow was far more spherical and symmetrical than the flattened disk of the Milky Way, and its energy signature didn't perfectly match any known astrophysical source. For a time, it looked like it could be the smoking gun, the precise signal expected from the annihilation of WIMP-like dark matter particles with a mass in the range of tens of giga-electronvolts. The excitement was palpable. Here, at last, was a potential signal written across the heart of our own galaxy. But science is a process of relentless scrutiny, and the story of the GVXS is a perfect case study. As the Fermi data accumulated over more than a decade, and as analysis techniques became more sophisticated, an alternative explanation gained significant traction. What if this glow wasn't from dark matter at all, but from a vast collection of thousands of unresolved millisecond pulsars? These are incredibly dense, rapidly spinning neutron stars that sweep beams of radiation across space like cosmic lighthouses, and they emit gamma rays in the exact same energy range. The galactic center is an old, crowded place, and it's entirely plausible that there exists a large population of these faint pulsars that our telescopes simply can't resolve as individual points of light. Their collective, blended glow could perfectly mimic the smooth, spherical signal we've been attributing to dark matter. The debate is far from settled. Some analyses claim the signal is too smooth to be pulsars, while others claim to see evidence of point-like sources within the glow. This mystery exemplifies the profound challenge of indirect detection, distinguishing a potential dark matter signal from the incredibly complex and vibrant background of ordinary astrophysics. It's a cosmic game of spot the difference where the stakes couldn't be higher, and the answer remains just out of reach, obscured by the very brilliance of the universe we can see. If you ever wanted a single, smoking gun image that proves the existence of dark matter beyond a reasonable doubt, you would find it in a spectacular cosmic collision known as the Bullet Cluster. Located about 3.8 billion light-years away, this system isn't a single, peaceful galaxy, but the violent aftermath of two massive galaxy clusters that have slammed into each other at a staggering speed of millions of miles per hour. When astronomers first pointed their telescopes at this region, they saw an incredible sight in the X-ray part of the spectrum. They found a huge cloud of superheated gas glowing brilliantly at temperatures of tens of millions of degrees. This gas is the ordinary baryonic matter that filled the space between the galaxies in each cluster. But in a collision, this intergalactic gas behaves just like the air in two clouds smashing together. It gets compressed, slowed down, and piles up in the middle. And that's exactly what the X-ray image showed, a central, bullet-shaped cloud of gas, which gave the cluster its name, where the two gaseous halos had collided and become stuck. The real magic, however, was revealed when astronomers mapped the cluster using a completely different technique, gravitational lensing. By observing how the mass in the cluster distorted the light from galaxies far behind it, they could create a precise map of where the actual mass, the source of the gravity, was located. The result was astonishing. The map showed that the vast majority of the mass was not in the center with the glowing, piled-up gas. Instead, it had passed right through the collision and was now in two distinct clumps far away on either side of the gas cloud. This was the decisive proof. The visible X-ray gas representing the ordinary matter had interacted electromagnetically and gotten stuck in the traffic jam of the collision. But the dominant mass, the dark matter, had simply sailed through the entire event as if the other cluster wasn't even there. It felt gravity, but it didn't feel friction, drag, or any other force. It was, for all intents and purposes, a ghost demonstrating perfectly its collisionless nature. This was not just inferred from galaxy rotations. This was a direct visual demonstration that most of the matter in the universe is something that does not interact with light or with itself in any way we can detect, other than through its relentless gravitational pull. The bullet cluster's importance cannot be overstated. It delivered a devastating blow to theories that tried to explain away dark matter by modifying the laws of gravity, like modified Newtonian dynamics or MEN. These theories propose that gravity works differently at very low accelerations, creating the illusion of extra mass without any actual dark stuff. But the bullet cluster created a situation that these theories struggle to explain. Here, the peak of the gravitational pull was completely divorced from the location of the ordinary matter. Modified gravity cannot easily create such a separation. The gravity should be strongest where the visible matter is most concentrated. The fact that the gravity was in one place and the normal matter in another proved that the mass causing the lensing was truly distinct and invisible. It had to be a form of matter that was fundamentally different from anything we know. Since the discovery of the bullet cluster, astronomers have gone on to find several other similar systems, with nicknames like the train wreck cluster or musket ball cluster, each showing the same telltale separation between mass and light. Each one is a natural laboratory, confirming the collisionless behavior of dark matter and tightening the case for its particle nature. But these cosmic collisions do more than just prove dark matter exists. They also allow us to test its specific properties with incredible precision. For instance, by studying the exact details of how the dark matter clumps moved through the collision, scientists can place limits on how much, if at all, dark matter particles might interact with each other. The fact that the clumps passed through so cleanly suggests that any such self-interaction must be extraordinarily feeble. If dark matter particles scattered off each other frequently, even a little, it would have created a drag effect, causing the dark matter halos to slow down, spread out, or lag behind. We don't see that in the bullet cluster, which tells us that dark matter is, at most, only very slightly social. Furthermore, by analyzing the geometry and speed of these mergers, we can even probe the velocity of dark matter particles. The way the halos behave is consistent with cold, dark matter particles that were moving slowly in the early universe, which is exactly what our standard cosmological model requires to form the intricate cosmic web we see today. So, these violent, billion-year-long car crashes in deep space are not just spectacular images. They are some of our most powerful and direct tools for studying the phantom that shapes the cosmos, giving us concrete data on the behavior of a substance we can neither see nor touch. Just when we thought we had a coherent picture of a universe inextricably woven together by dark matter, astronomers stumbled upon a series of cosmic outliers so bizarre they seemed to break all the rules. Imagine discovering a bustling city that somehow floats in the sky without any visible means of support, defying gravity itself. This is the level of shock that rippled through the astrophysics community with the identification of galaxies like NGC 1052 DF2 and DF4. These are ultra-diffuse galaxies, immense in size but ghostly in appearance, containing very few stars. The initial measurements of their internal motions, however, delivered the real bombshell. The stars within them were moving surprisingly slowly. In a universe dominated by dark matter, such sluggish stellar velocities should be impossible. The calculations showed that the total mass required to account for these gentle motions was almost exactly equal to the mass of the visible stars themselves. There appeared to be no room left for a massive, invisible dark matter halo. These galaxies, according to the data, were made almost entirely of ordinary matter. It was as if we had found a skeletal system that could walk and talk without any bones. This revelation was profoundly unsettling because it directly contradicted the central role dark matter is supposed to play. For decades, our story has been that dark matter acts as the gravitational anchor, forming first and providing the necessary scaffolding for ordinary matter to collapse and form stars. The existence of a galaxy with no dark matter turns this narrative on its head. If dark matter is truly essential, how could a galaxy form without it? It would be like building a skyscraper without its steel frame, using only the glass and interior walls. The discovery forced astronomers to confront a radical possibility: that galaxy formation might be a more complex and diverse process than our models suggest, and that under certain rare circumstances, collections of stars can indeed come together without the guiding hand of a dark matter foundation. Of course, a finding this extraordinary immediately triggered intense scrutiny and a fierce scientific debate. The central question was whether these galaxies were truly devoid of dark matter, or if we were being misled by errors in our observations. The most critical point of contention revolved around distance. To determine a galaxy's mass, you need to know two things: how fast its stars are moving and how far away it is. A miscalculation in distance can throw off the entire mass estimate dramatically. The initial studies placed NGC 1052DF2 at a specific distance that led to the startling low mass conclusion. However, other research teams, using different measurement techniques, argued for a significantly closer distance. If they are correct, the galaxy would be smaller and intrinsically dimmer, meaning the stars we see are actually fainter and less massive than first assumed. To explain the observed starlight with lower mass stars, the galaxy would need to contain a substantial amount of unseen mass of dark matter. After all, this debate over a few tens of millions of light years highlights the incredible difficulty of cosmic cartography and how our entire understanding of an object's nature can hinge on a single, hard-to-measure number. Beyond distance, the methods used to weigh the galaxy were also picked apart. The mass is inferred by observing the motions of star clusters orbiting within the galaxy. If these clusters are not truly bound to the galaxy, but are instead merely passing by in the foreground or background, or if we are seeing a temporary, unrepresentative state, then the velocity measurements would be meaningless. Critics argued that with so few bright traces to track, the data was simply too sparse to draw such a monumental conclusion. Proponents of the dark matter-free hypothesis counter that they have accounted for these uncertainties and that the evidence remains robust. This back and forth is science at its most vital, a rigorous, meticulous process where extraordinary claims are subjected to relentless testing by the entire community, with the goal of arriving at a truth that can withstand all challenges. Let's assume for a moment that these strange galaxies are confirmed to be as devoid of dark matter as they appear. How could such a thing even happen? One of the most compelling theories involves a dramatic and violent galactic encounter. Imagine a small, nascent galaxy beginning its life with a normal complement of dark matter, happily forming its first stars. Then it has a fateful, close encounter with a much larger, more massive galaxy. The smaller galaxy gets caught in the larger one's gravitational tide. Now, dark matter and ordinary matter respond to this tidal force in different ways. The dark matter, which is collisionless and spread out in a large halo, is more loosely bound. As the small galaxy swings by, the tidal forces can effectively strip away this diffused dark matter halo, pulling it out into long streams in intergalactic space. The ordinary matter, the gas and stars, is more concentrated and clumpy. it can resist being torn away, remaining as a coherent, though now isolated, collection of stars. The result is a galaxy that has been tidally stripped of its dark matter, leaving behind a pure batch of luminous matter, a ghost ship sailing through space after losing its invisible anchor. Another fascinating, though more speculative, idea is that these galaxies formed in a truly unique way, directly from the debris of a cosmic collision. When two large galaxies smash into each other, vast streams of gas can be pulled out from them. In the tumultuous wake of such a collision, this gas could theoretically collapse under its own gravity and form new stars, creating a galaxy that is born after the main dark matter structures have already formed. This second-generation galaxy would condense out of the ordinary matter that was ejected in the crash and could potentially end up with very little dark matter of its own, having been assembled from material that was already separated from its original dark matter halo. Both of these formation scenarios transform these oddball galaxies from rule-breaking anomalies into cosmic forensic evidence. They become natural, if rare, products of the violent interactions that shape galactic evolution, demonstrating that dark matter and normal matter can, under the right conditions, be pulled apart. The existence of dark matter-free galaxies, if finally proven, would actually be a brilliant confirmation of the dark matter particle hypothesis, while simultaneously dealing a heavy blow to alternative theories of gravity like men. This seems counterintuitive at first, but the logic is powerful. If you want to prove that dark matter is a real, physical substance that can be moved around, what better evidence could you have than finding places where it's missing? In the dark matter paradigm, its distribution is not perfectly uniform. It can be clustered in some areas and absent in others, just like ordinary matter. Finding a galaxy without it is, in a strange way, the ultimate proof that it is a separable, tangible component of the universe. On the other hand, theories like modified Newtonian dynamics, which explain galactic rotation by changing the laws of gravity rather than invoking invisible matter, face a severe challenge. If gravity is simply modified, then its effect should be universal. Every galaxy should show the same kinematic signatures without exception. The discovery of even one galaxy that rotates perfectly according to Newton's original laws without any need for dark matter or modified gravity is a devastating anomaly for men. It suggests that the missing mass really is a substance that can be present or absent, not an immutable law of physics. So, the intense study of these seemingly paradoxical galaxies, from the fierce debates over their distances to the creative theories about their origins, is far more than academic squabbling. It is a crucial stress test for our most fundamental ideas about the cosmos. Whether they are ultimately confirmed as truly dark matter-free or are reclassified as more conventional objects, the journey of discovery they have prompted has already deepened our understanding. They have forced us to sharpen our observational techniques, to refine our models of galaxy formation, and to consider more creative and dynamic cosmic histories. They stand as a powerful reminder that the universe is under no obligation to be simple, and that its greatest mysteries are often hidden not in the overwhelming patterns, but in the startling, rule-breaking exceptions. This cosmic uncertainty over whether the universe will end with a long, quiet fade or a sudden, violent tear leads us directly to one of the most profound and personal questions we can ask about our place in the cosmos. What does it all mean for us? The nature of dark energy isn't just a technical detail for cosmologists. It's the script for the ultimate fate of every galaxy, every star, every planet, and every living thing that will ever exist. Let's trace out these possible endings, starting with the scenario that many scientists currently consider the most likely. If dark energy is indeed a true cosmological constant, an unchanging, gentle pressure inherent to the vacuum of space, then the universe is on a one-way trip toward a state known as the heat death or the Big Freeze. In this future, the acceleration continues at a steady, unrelenting pace. First, galaxies outside our local gravitationally bound group will recede until their light is stretched so far into the red that it becomes undetectable, and then they will vanish beyond our cosmic horizon entirely. The universe will become a collection of isolated island universes, each one drifting alone in an ever-expanding void. Over trillions of years, the stars within our own galaxy will slowly burn through their fuel. New star formation will cease as the last reserves of interstellar gas are either consumed or blown away into the intergalactic darkness. One by one, the stellar furnaces will flicker and die, leaving behind a cosmic graveyard of black holes, neutron stars, and cold, dead white dwarfs. Even these remnants won't last forever. Over almost unimaginable timescales, even protons, the very building blocks of atomic nuclei, may decay, and black holes will slowly evaporate due to Hawking radiation. The final state would be a universe that is utterly dark, cold, and empty, a thin, uniform soup of fundamental particles and radiation, stretched so thin that no meaningful energy transfers can ever occur again. It is a quiet, desolate, and eternal end. But what if the cosmological constant is not the final answer? The possibility that dark energy is a dynamic field known as quintessence opens the door to far more dramatic and abrupt conclusions. The most terrifying of these is the Big Rip. Imagine if the strength of dark energy isn't constant, but instead grows stronger over time. In this scenario, the acceleration doesn't just push galaxies apart. It becomes an overwhelming, dominant force that eventually overcomes every single force that holds things together. The end would not be a slow fade, but a catastrophic, rapid unraveling of reality itself. First, the gravitational bonds connecting galaxy clusters would be severed. Then, the expansion force would exceed the gravity holding individual galaxies together. Stars would be flung from their galaxies into the void. As the repulsive force intensifies, it would then target the very systems that give us light and life. Planetary systems would be torn apart, with planets ripped from their orbits around their stars. In the final, horrifying moments, the force would become so powerful that it would overcome the electromagnetic forces holding your very body together. Molecules, atoms, and even atomic nuclei would be shredded into a diffuse, disconnected cloud of fundamental particles. In a matter of moments, the entire structure of the universe would be annihilated. The timeline for such an event is purely speculative, but some models suggest it could happen in as little as 22 billion years from now, a blink of an eye on the cosmic scale. This is an ending defined not by cold and darkness, but by ultimate, violent disintegration. There is a third, more cyclical possibility, one that offers a strange kind of cosmic comfort. What if dark energy, this repulsive force, isn't permanent? What if it slowly decays away or even reverses its nature, becoming an attractive force? This could lead to a big crunch, a poetic inversion of the Big Bang. In this scenario, the acceleration would eventually cease. The expansion of the universe would slow, halt, and then reverse. Galaxies would begin rushing back toward one another. The background temperature of the universe, which has been dropping since the beginning, would start to rise again. The night sky would gradually brighten as distant galaxies blue shift, their light compressing into more energetic wavelengths. The collapse would accelerate, with galaxies merging in colossal, fiery collisions. The universe would heat up to the point where atoms are torn apart, and then even atomic nuclei dissociate into a searing plasma. All structure and complexity would be erased as everything is compressed into an infinitesimally hot, dense singularity, a state that might then, according to some speculative theories, trigger a new Big Bang, birthing a brand new universe in an endless cycle of cosmic death and rebirth. This idea of a phoenix universe constantly recycling itself is a powerful narrative that has captivated philosophers and scientists alike, suggesting that our entire cosmos might be just one episode in an infinite, timeless series. These wildly different destinies force us to confront deep philosophical questions about meaning, legacy, and our own fragile existence. In a universe headed for a heat death, all structure, all information, all memory of what once was will eventually be erased. Every achievement, every work of art, every life that was ever lived will leave no permanent trace. This can feel profoundly nihilistic, suggesting that in the grand scheme of things, nothing ultimately matters. Yet it can also be seen as liberating. It places an immense value on the here and now, on the fleeting beauty and complexity that exists in this cosmic moment. Our lives, our civilizations, and our planet become all the more precious precisely because they are temporary, brilliant sparks in an otherwise dark and endless night. The Big Rip, by contrast, is a fate that feels almost malevolent, a universe that actively destroys itself. It raises the unsettling possibility that the fundamental laws of physics are not just indifferent to us, but are ultimately hostile to the very existence of complex structure. The cyclical universe of the Big Crunch offers a different kind of meaning, one of potential eternity and renewal. While our specific universe would end, the story would continue. The laws of physics might be slightly different in each new cycle, perhaps allowing for an infinity of possibilities to play out over endless time. Our existence in such a cosmos could be part of a pattern grander than we can possibly imagine. The key that unlocks which of these fates is our true destiny lies in the precise nature of dark energy. This is not a question that will remain philosophical forever. It is a question that observational astronomy is actively working to answer. The great cosmic surveys of the next decade, like the Vera Rubin Observatory and the Nancy Grace Roman Space Telescope, are designed to measure the expansion history of the universe with unprecedented precision. By tracking billions of galaxies and thousands of supernovae, they will determine if the strength of dark energy has remained constant over the last several billion years, or if it has been changing. If it's constant, the long, cold fade of the heat death becomes our most probable future. If it is growing stronger, we must seriously consider the reality of a big rip. If it is found to be weakening, it could open the door once more to a cyclical cosmos. We are living in a pivotal moment, a brief window in cosmic history where intelligent life has arisen and developed the capacity to not only observe the universe but to understand its past and predict its ultimate end. The mystery of dark energy is therefore the ultimate detective story, a quest to read the final page of the cosmic book before the story is over, giving us a say in understanding the grand narrative of which we are an infinitesimal yet uniquely conscious part. Just when we think we have a clean, elegant picture of the early universe, it throws us another curveball, and this one is so perplexing it's been given a name straight out of a conspiracy thriller, the axis of evil. This mystery takes us back to the cosmic microwave background, that pristine baby picture of the cosmos. The fundamental assumption of modern cosmology, known as the cosmological principle, states that the universe is isotropic and homogeneous on the largest scales. In simple terms, this means it should look the same in every direction, with no preferred axis, no up or down to the cosmos. It shouldn't have a north or south pole. But when scientists meticulously analyzed the most detailed maps of the CMB from the Planck satellite, they found hints of something that seems to defy this very principle. Large-scale features in the temperature fluctuations, the hot and cold spots that seeded all future structure, appear to be subtly aligned along a particular preferred direction in space, a kind of cosmic axis. This unexpected alignment is what's dramatically been dubbed the axis of evil, and if it's real, it suggests that the universe might have a fundamental handedness, a lopsidedness we never anticipated. The anomalies themselves are incredibly subtle and are found by performing complex statistical tests on the CMB data. One of the key pieces of evidence is an alignment between the quadrupole and octupole moments of the CMB. These are just fancy terms for specific patterns of hot and cold spots on different angular scales. In a perfectly random, isotropic universe, these patterns should be oriented randomly with respect to each other and to our own solar system. But the data suggests they aren't. They seem to be correlated, and their plane of symmetry aligns suspiciously well with the plane of our solar system, and even the direction of our galaxy's motion through space. This is deeply strange. It's as if the grandest blueprint of the entire cosmos has a faint watermark that somehow knows about our little local neighborhood, creating a cosmic coincidence that feels profoundly unsettling. Why should the largest possible structures in the universe care about the orientation of our modest solar system? It's like finding that the foundation of a continent-sized skyscraper was poured with a slight tilt that just happens to point directly at your house. The immediate and most conservative explanation is that this is all just a monumental statistical fluke. We are, after all, trying to extract incredibly faint signals from a very noisy and complex dataset. Perhaps when we look at the one universe we can observe, we are simply seeing a random pattern that, by pure chance, looks aligned. It would be like rolling a die 100 times and getting a 6 every single time. It's incredibly unlikely, but not strictly impossible. Many scientists lean towards this explanation, arguing that the significance of the anomaly has diminished somewhat with the latest, more precise data from the Planck mission. They suggest that better foreground modeling accounting for the dust and gas in our own Milky Way that contaminates the pristine CMB signal might eventually erase the anomaly entirely. In this view, the axis of evil is a ghost in the machine, a tantalizing mirage created by the limitations of our own measurements and our human tendency to find patterns even where none exist. However, if the alignment persists and is confirmed to be real, the implications are revolutionary, pointing toward physics beyond our standard model. One extraordinary possibility is that this preferred axis is a fossil relic from the era of inflation, that period of faster-than-light expansion in the universe's first instant. Perhaps the inflationary field that drove this expansion was not perfectly uniform, but had a slight directional preference, a kind of cosmic grain, like the grain in a piece of wood. This would have imprinted a subtle anisotropy on the very fabric of space-time, a preferred direction that was then frozen into the CMB. Another, even more mind-bending idea connects the axis to the mysterious nature of dark energy or even the fabric of space-time itself. Could it be that the vacuum of space has a fundamental structure that breaks perfect isotropy? Or perhaps this alignment is a clue that our universe experienced a more complex birth than a single, simple Big Bang, possibly involving collisions with other universes in a vast multiverse. This last idea is perhaps the most spectacular of all. The multiverse hypothesis suggests that our universe is just one bubble in a frothing, infinite cosmic foam of other universes, each with its own physical laws. If our universe formed near another one, or even collided with a neighboring bubble in the greater multiverse, the gravitational influence of that other universe could have tugged on the fabric of our own cosmos, leaving a permanent scar, a directional imprint on our CMB. The axis of evil in this scenario would be the first observational evidence that we are not alone in the ultimate sense that our entire universe is part of a much grander, more complex structure. It would be a bruise on the sky, a cosmic fingerprint from a reality beyond our own, telling us that the Big Bang was not the absolute beginning, but merely a local event in a much wider and stranger metacosmos. The search for the truth behind the axis of evil is far from over. It drives the design of future CMB experiments that will map the polarization of this ancient light with even greater precision, hunting for the definitive signature that will tell us if we're seeing a statistical phantom, a crack in our standard model, or our first fleeting glimpse into the multiverse. For nearly a century, the scientific community has largely agreed on a single, powerful narrative to explain the universe's missing mass, a vast, invisible ocean of dark matter particles. But what if that entire story is wrong? What if we're not missing matter, but are instead misunderstanding a fundamental force? This brings us to one of the most audacious and compelling rival ideas in all of modern physics, a theory that dares to rewrite the laws of gravity themselves. It's called modified Newtonian dynamics, or MND, and it proposes a radical alternative. Instead of filling the cosmos with phantom particles we cannot find, perhaps we just need to realize that gravity doesn't work quite the way we thought it did in the faint, sprawling outskirts of galaxies. The spark for this idea came in the early 1980s from physicist Mordechai Milgrom, who was deeply troubled by the galaxy rotation problem. He noticed something fascinating and highly specific. The anomalous flatness of galaxy rotation curves always became apparent in regions of extremely weak gravity, where the acceleration dropped below a certain, very tiny threshold. This was a crucial clue. What if, Milgrom wondered, Newton's famous law of universal gravitation, a law tested impeccably here in our solar system, simply breaks down at these incredibly low accelerations? His proposed modification was elegantly simple. He suggested that while Newton's and Einstein's laws hold perfectly true in high acceleration environments, like the orbits of planets around our Sun, the force of gravity takes on a different form where its pull becomes extraordinarily feeble. In this deep MND regime, the force would switch from its familiar inverse square law to a simpler inverse distance relationship. This tiny tweak in the math has a monumental consequence. It predicts that stars orbiting far from a galaxy's center will naturally maintain high speeds, perfectly producing the flat rotation curves that had baffled astronomers, and all without a single particle of dark matter. The appeal of MND is undeniable, where the dark matter model requires us to carefully tailor the distribution of an invisible substance for each individual galaxy to match its rotation curve. MND does something almost magical. It predicts the outcome from the visible matter alone. For many galaxy types, especially isolated spiral galaxies, it works astonishingly well with essentially no free parameters. It's a beautifully economical solution, solving the rotation curve problem, not by adding a mysterious, dominant new ingredient, but by suggesting a subtle refinement to a force we thought we knew inside and out. This success makes it far more than just a fringe idea. It's a robust, mathematically precise alternative that has forced the entire physics community to sit up and take notice, presenting a clear philosophical choice. Is the universe filled with ghosts, or are we just reading the rules of gravity incorrectly? However, no grand scientific theory can survive on a single success, and this is where the battle truly intensifies. While MND excels at explaining the dynamics within individual galaxies, it stumbles catastrophically when faced with the large-scale architecture of the cosmos. Recall the bullet cluster, that spectacular colliding system where the gravitational lensing map showed the mass had sailed clean through the collision, completely separated from the visible gas. This observation is a devastating blow to MND's core premise. Modified gravity theories intrinsically link the gravitational force to the distribution of visible matter. The gravity should be strongest where the stars and gas are most concentrated. The bullet cluster presents an irrefutable case where the gravity is in one place and the normal matter is in another. It's direct, visual proof that the source of gravity can be completely divorced from the stuff we can see, something that is virtually impossible for MND to explain without, ironically, invoking some form of invisible matter to account for the misplaced mass. The challenges for MND only compound when we look back in time to the infant universe. The intricate pattern of hot and cold spots in the cosmic microwave background is a precise record of the gravitational struggles in the primordial cosmos. Our standard model of cosmology, lambda cold dark matter, uses a specific mix of dark matter, dark energy, and ordinary matter to run a computer simulation of the universe's evolution, and it reproduces this CMB pattern with breathtaking accuracy. MND, in its original form, has no such narrative for the early universe. The oscillations in the primordial plasma that imprinted the CMB spots rely critically on the gravitational influence of dark matter to grow properly. Without that extra gravitational source, the models struggle to create the observed level of structure. Furthermore, WIMPs says nothing about the accelerating expansion of the universe driven by dark energy, forcing its proponents to somehow graft that observation onto their models separately. To account for these cosmic scale phenomena, even the most ardent WIMP supporters have been forced to develop hybrid models like tensor vector scalar gravity, which incorporate additional fields that, in practice, behave very much like a form of dark matter and dark energy. This has led critics to argue that WIMP, in its quest to avoid dark matter, often ends up proposing something that looks just as complex and invisible. So, where does this grand battle leave us? We are faced with two profoundly different visions of reality. On one side, the prevailing lambda cold dark matter model is a stunningly successful big-picture theory. It explains the cosmic microwave background, the large-scale structure of the universe, the behavior of galaxy clusters, and the accelerating expansion, all within a single, coherent framework. Its major weakness is the decades-long, frustrating failure to directly detect the dark matter particle that serves as its foundation. On the other side, WIMP provides an elegantly simple and highly successful description of the internal dynamics of galaxies, something the dark matter model handles with more difficulty. Its major weakness is its inability to explain the cosmos on the largest scales without incorporating elements that mimic the very substances it seeks to replace. This isn't just an academic debate, it's a high-stakes struggle at the very frontier of physics. The persistence of WIMP acts as a crucial check on scientific overconfidence, a constant reminder that our understanding is never complete. It forces the mainstream to sharpen its arguments, to explain why dark matter is truly necessary, and to redouble efforts to find it. The ultimate resolution may not be a simple victory for one side. It's possible that the final theory will incorporate insights from both. Perhaps dark matter does exist, but its effects are modulated by a slight modification to gravity under certain conditions. Or perhaps a completely new understanding of space-time will emerge that makes sense of both galactic rotations and cosmic collisions in a way we haven't yet imagined. This ongoing battle between unseen particles and rewritten laws is more than a disagreement. It is the vibrant, contentious, and utterly essential process of science at work, pushing itself to its limits in pursuit of a deeper truth about the fundamental nature of our universe. For so long in our cosmic story, dark matter has been portrayed as the silent, dominant architect, while ordinary matter, the stuff of stars, planets, and us, has been cast as a passive passenger, simply falling into the gravitational pits that dark matter provides. But this tidy division is starting to look like a vast oversimplification. It turns out that the so-called normal matter, what scientists call baryonic matter, is far from well-behaved. In fact, it's incredibly volatile, and its dramatic outbursts might hold the key to solving some of dark matter's most stubborn puzzles. This is the complex and often messy world of baryonic feedback, a process where the universe's visible components talk back to the invisible framework, reshaping the cosmic landscape in profound ways. Think of a newborn galaxy in the early universe. It's a vast cloud of dark matter, and within its gravitational embrace, a huge reservoir of hydrogen and helium gas has begun to cool and condense. The first generation of stars ignites, and these aren't like our steady, middle-aged sun. Many of them are behemoths, monsters dozens of times more massive, living fast and furious lives that last only a few million years. Their deaths are not quiet affairs. They explode as supernova, detonating with the energy of billions of nuclear bombs. These explosions do more than just light up the cosmos. They flood their surroundings with intense radiation and blast waves of searing hot gas, creating powerful winds that can rush through the galaxy at thousands of kilometers per second. This is the most basic form of baryonic feedback. In a small, fragile dwarf galaxy with a relatively weak gravitational grip, these collective blasts can be catastrophic. They can literally blow the entire remaining reservoir of star-forming gas clean out of the galaxy, permanently shutting down its ability to make new stars and leaving it a faint, dormant relic. But the influence of this feedback doesn't stop with the gas. This is where the story gets really interesting for dark matter. While dark matter particles don't feel the blast wave's pressure or the radiation's heat directly, they are exquisitely sensitive to gravity. When supernovae violently eject enormous clumps of mass, the gas out of the central regions of a galaxy, they are dramatically and suddenly altering the galaxy's gravitational landscape. Imagine a dense crowd of people standing in a deep, smooth pit. Now imagine if a large group in the very center suddenly vanished. The shape of the pit would change, the steep sides would slump inward, becoming shallower and gentler. This is, in gravitational terms, what happens to the dark matter halo. As massive amounts of baryonic matter are pumped outwards by these explosions, the gravitational potential well becomes less steep. The dark matter particles, responding solely to this changing gravity, naturally migrate outwards, relaxing into a new, more spread-out configuration. This process, repeated over billions of years across countless cycles of star formation and death, could very well be the mechanism that erases the predicted sharp central cusp of dark matter and replaces it with the soft, flat core that astronomers actually observe in many dwarf galaxies. The cuspy halo problem, once a major headache, may find its solution not in the nature of dark matter itself, but in the explosive tantrums of the first stars. But stars are not the only actors on this stage. An even more powerful source of baryonic feedback comes from the very heart of the most massive galaxies, where a supermassive black hole resides. Most of the time, these cosmic monsters are quiet, but when they actively feed on surrounding gas, they become what we call active galactic nuclei. This feeding frenzy is not a gentle process. As matter spirals down into the black hole's event horizon, it doesn't go quietly. Intense magnetic fields can funnel some of the infalling material into jets of plasma that shoot out from the poles at nearly the speed of light, while radiation and winds blast out in all directions. The energy released by a single, bright quasar can outshine its entire host galaxy. This incredible outpouring of energy acts as a cosmic thermostat. It heats the surrounding gas to such extremes that it cannot cool and collapse to form stars, effectively halting the galaxy's growth. Furthermore, these jets and winds can push the galactic gas around with phenomenal force, and just like with supernova feedback, this movement of immense mass tugs gravitationally on the dark matter halo, potentially smoothing out its central density and limiting the growth of the very largest structures. This could provide an elegant explanation for the too big to fail problem. The most massive dark matter halos, which should have easily become brilliant, dominant satellite galaxies, may have had their star formation violently quenched by the furious feedback from their central black holes, leaving them as the dark, failed giants we struggle to find today. Incorporating this chaotic reality into our pristine supercomputer simulations is one of the grand challenges of modern cosmology. The old models that treated baryons as simple, cold gas are being replaced by a new generation of virtual universes that try to simulate the complex physics of supernova blasts, black hole accretion, and interstellar turbulence. These new simulations, with names like Illustris TNG and Eagle, are revealing a universe that is far more dynamic and interconnected. They show that baryonic feedback isn't just a minor detail, it's a fundamental governing process. It regulates how many stars a galaxy can form, determines its final size and shape, and crucially, sculpts the very distribution of the dark matter that started it all. This creates a fascinating and complex dialogue between the dark and light sectors of the universe. Dark matter provides the initial gravitational blueprint, but once baryons arrive on the scene and start lighting their fires, they begin to remodel the foundation, sanding down the sharp corners and rearranging the furniture. The universe we see today is not just a product of dark matter's pull. It is the result of a billions of years-long gravitational conversation, a cosmic dance between the invisible and the luminous, where the smallest, brightest sparks have the power to reshape the largest, darkest structures. One of the most dramatic and captivating alternatives to the particle zoo of WIMP and axions suggests that dark matter isn't made of tiny, elusive particles at all, but of the most gravitationally powerful objects in the universe, black holes. Not the black holes we know, which form from the collapse of massive stars, but something far older and more exotic primordial black holes. This hypothesis proposes that in the incredibly dense, chaotic furnace of the universe's first second, microscopic fluctuations in density could have been so extreme that pockets of space-time simply collapsed directly into black holes. These would not be tied to the life cycle of stars. They would be fossils from the moment of creation itself, and if they formed in vast numbers, they could, in principle, constitute the entire dark matter budget of the cosmos. Imagine a galaxy like our Milky Way, its vast halo not filled with a cloud of invisible particles, but instead swarming with countless trillions of these ancient dark relics, each one a tiny, concentrated knot of pure gravity from the dawn of time. For this idea to work, however, these primordial black holes would need to survive for 13.8 billion years without evaporating due to Hawking radiation, and they would have to fit within a very specific range of masses. If they were too small, say the mass of a mountain or less, they would have evaporated away by now in a flash of radiation. If they were too large, with masses comparable to stars, we would have seen their disruptive effects on the structure of star clusters and the delicate fabric of the cosmic microwave background. For decades, the most promising window was for black holes around the mass of a large asteroid, perhaps a billion kilograms. This is a fascinating mass range because objects of this size would act as cold dark matter, but they are too small to form any kind of luminous accretion disk, rendering them completely black. The primary way to detect such an object would be through a phenomenon called gravitational microlensing. If a primordial black hole of this mass were to pass directly between Earth and a distant star, its gravity would act as a lens, briefly bending and focusing the star's light, causing it to flare in brightness for a few minutes or hours before fading back to normal. Astronomers have conducted massive, automated microlensing surveys, most famously with projects like the optical gravitational lensing experiment, to search for these telltale flashes across millions of stars. The results have been both constraining and fascinating. They have largely ruled out the possibility that primordial black holes in the mass range of a large asteroid all the way up to about 10 times the mass of Jupiter could make up all of the dark matter. The universe is simply not filled with enough of these lensing events. If such black holes were 100% of the dark matter, we would see stars flickering all the time. The fact that we don't means that this particular mass range is, at best, only a minor contributor to the overall dark matter budget. It was a major blow to the simplest versions of the primordial black hole hypothesis, seemingly closing a huge swath of potential parameter space and pushing the idea to the fringes of cosmology. But then, in 2015, the LIGO Observatory made history by directly detecting gravitational waves for the first time, from the merger of two black holes, each about 30 times the mass of our Sun. This discovery sent a shockwave through the astrophysics community, and it immediately resurrected the primordial black hole hypothesis in a new and exciting form. The black holes LIGO detected were surprisingly heavy for stellar remnants. While it's possible they formed from massive stars in a dense environment, their unusual mass sparked a compelling question: what if they weren't stellar in origin at all? What if they were primordial black holes formed in the Big Bang that had been orbiting each other for billions of years before finally colliding? If true, this would mean that a significant population of black holes exists in this intermediate mass range from a few solar masses up to perhaps 100. The LIGO and Virgo collaborations have since detected dozens of such mergers, and while many can be explained by conventional stellar evolution, the possibility remains that a fraction of them are these primordial ancients. The constraints here are different from the microlensing surveys. It turns out that if all the dark matter were made of black holes in this 30 solar mass window, they would have disrupted wide binary star systems in a way we do not observe. So, just like with the asteroid mass objects, they cannot be the whole story. However, a population constituting even a few % of the dark matter is still entirely possible and would be a monumental discovery. So, where does this leave the grand idea? The observational data has effectively squeezed the primordial black hole hypothesis from both sides, but it has not killed it. Instead, it has carved out a few narrow and tantalizing windows where these ancient objects could still be hiding. One promising window is for very, very light black holes with masses similar to a small asteroid or even a large mountain. These would be so numerous that they would behave more like a fluid or a wave of gravity than individual objects, and they are much harder to rule out with current microlensing surveys. Another window exists for truly colossal primordial black holes with masses thousands or even millions of times that of our Sun. These would be so rare that we might not have seen one yet, but they could explain the mysterious origins of the supermassive black holes that squat at the centers of galaxies, objects that appear too early in the universe to have grown from mere stellar seeds. The most likely scenario is that dark matter is not a single thing, but a mixture. Perhaps the bulk of it is an as yet undiscovered particle like an axion, while a fascinating minority component is made of these primordial black holes. The gravitational wave chirps from LIGO being the first hints of their shadowy existence. The future of this search is incredibly exciting. The next generation of microlensing surveys, like those planned with the Vera Rubin Observatory, will monitor billions of stars with unprecedented precision, capable of detecting even shorter, fainter flares that could betray the passage of Earth mass black holes. Meanwhile, the LIGO-Virgo-CAGRA network of gravitational wave detectors will accumulate more and more merger events, allowing statisticians to look for the unique clustering and mass distribution that would be the signature of a primordial population, distinct from the black holes born from stars. If a black hole merger is ever detected where one of the objects is clearly too light to have formed from stellar collapse, or if we find a black hole orbiting in a place where no star could have possibly existed, it would be powerful, albeit indirect, evidence for this hypothesis. The quest to determine if dark matter is made of primordial black holes is a perfect example of how science operates at the frontier. An elegant, old idea is confronted with hard data, which forces it to evolve, adapt, and find new, more subtle ways to survive. It may not be the complete answer, but the possibility that the dark side of our cosmos is littered with these microscopic fragments of the Big Bang remains one of the most thrilling and dramatic possibilities in all of modern physics. This relentless acceleration driven by dark energy leads us to one of the most conceptually challenging and isolating futures we can imagine, a reality where the universe actively erases its own history. The idea hinges on a subtle but crucial distinction in how we understand the expansion of space itself. You might have heard that nothing can travel faster than the speed of light, and that's true for objects moving through space. But space itself, the very fabric of the cosmos, is under no such restriction. It can stretch and expand at any rate it likes. As dark energy pushes the universe to expand at an ever-increasing pace, there will come a point for every distant galaxy where the space between us and it is stretching so fast that the light leaving that galaxy, even though it's traveling at light speed toward us, will be carried away from us by the expansion. It's like a child trying to run the wrong way on a moving walkway that's accelerating. No matter how fast they run, the platform is moving them backward faster. At that moment, that galaxy will vanish from our view, passing beyond what cosmologists call our cosmic horizon. Its light will simply never reach us again. It hasn't been destroyed, it's been placed forever out of reach, receding into a privacy from which it can never emerge. The implications of this are staggering, not just for the far future, but for the very practice of science and the preservation of cosmic knowledge. Imagine a future astronomer born in our Milky Way galaxy trillions of years from now. They will look up at a night sky that is profoundly, unnervingly empty. All the galaxies that currently form the great cosmic web will be long gone, having crossed that horizon one by one. The only objects left in their sky will be the aging stars of our own local group, a small collection of galaxies, including Andromeda, that are gravitationally bound to us and thus immune to the expansion-driven exodus. For this future scientist, the universe will appear to be a single, static island in an infinite black void. They will have no evidence of the expansion of the universe, no redshift to measure from other galaxies, and crucially, no cosmic microwave background radiation. That faint afterglow of the Big Bang, our most important piece of evidence for the universe's hot, dense beginning, will have been stretched to such long wavelengths that its photons will be undetectable, their energy dissipated into a whisper too faint to hear against the background noise of the cosmos. The most fundamental pillars of our modern cosmology will have simply vanished from sight. This creates a deeply philosophical and almost tragic scenario. That future civilization, no matter how advanced, would be fundamentally cut off from the true nature of the cosmos. Without the redshift of distant galaxies, they would have no reason to believe in an expanding universe. Without the cosmic microwave background, they would have no clue about the Big Bang. They might develop a completely different and entirely wrong model of reality, perhaps concluding that the universe is eternal and static, with their small cluster of galaxies as its entirety. All the hard-won knowledge we have accumulated over the last century, the discovery of an expanding universe, its explosive origin, the existence of dark energy, would be lost not through a cataclysm, but through the silent, inexorable working of the universe's own laws. The evidence for the greatest story ever told will have been systematically erased, leaving future intelligences in a state of permanent cosmic ignorance, unaware of the vast, dynamic, and interconnected cosmos that once was. This isn't just a distant, abstract thought experiment. It has consequences for our own understanding today. It tells us that we are living in a uniquely privileged moment in cosmic history, a golden age of cosmology. Right now, just over 13 billion years after the Big Bang, the universe is transparent enough and the expansion is still slow enough that we can see the key evidence. We can detect the cosmic microwave background. We can measure the redshifts of billions of galaxies. We can observe the large-scale structure. We are in a narrow window of time where the universe is old enough to have developed complex structures and intelligent life, but young enough that the clues to its origin and evolution are still visible. This cosmic horizon is steadily closing in on us, and in a future dominated by dark energy, that window will slam shut forever. Our ability to do cosmology, to understand the universe on its grandest scales, is therefore not a permanent feature of reality, but a temporary opportunity, a fleeting glimpse of the cosmic dawn before the long, dark night sets in. It imbues our current scientific quest with a profound urgency and significance as we race to decipher the universe's secrets before they fade from view for all time. Meanwhile, deep within the esoteric world of particle physics, a completely different kind of puzzle was unfolding, one that, on the surface, seemed to have nothing to do with the rotation of galaxies or the fate of the cosmos. This is the strong CP problem, and it is considered one of the most fine-tuned and inexplicable mysteries in the entire standard model of particle physics. To grasp it, we need to understand two things: the strong nuclear force, which glues quarks together to form protons and neutrons, and a subtle symmetry called CP. CP stands for charge and parity. Imagine taking a particle and replacing it with its antiparticle. That's the charge conjugation part, and then viewing its interactions in a mirror which flips its spatial coordinates. That's the parity part. For most of the forces in nature, this combined CP symmetry is respected. The laws of physics look the same if you do this swap. However, we know that the weak nuclear force responsible for radioactive decay violates CP symmetry in a small but measurable way. This is a good thing. It's part of the reason our universe is made of matter and not antimatter. The puzzle is that the strong nuclear force, incredibly, appears to respect CP symmetry perfectly. According to the mathematics of the Standard Model, there is absolutely no reason it has to. The theory naturally allows for a term that would violate CP in the strong force, a term characterized by an angle mysteriously called theta. This angle could, in principle, be any value. If it were anything other than zero, the strong force would violate CP. The consequences of this would be dramatic and bizarre. For instance, it would cause the neutron, which is electrically neutral, to possess a tiny but measurable electric dipole moment, a kind of internal separation of positive and negative charge, making it behave like a microscopic compass. Physicists have hunted for this neutron electric dipole moment with extreme precision. Their results show that if it exists at all, it is so infinitesimally small that the theta angle must be fantastically close to zero. This is the strong CP problem in a nutshell. Why is this fundamental parameter of the universe so exquisitely tuned to zero, when every known principle suggests it should be a random, noticeable number? It's as if a fundamental dial on the universe's control panel has been set to zero with unbelievable precision, and we have no idea who set it or why. In the 1970s, a brilliant solution was proposed by Roberto Pexi and Helen Quinn. They suggested that this theta angle isn't a fixed fundamental constant at all. Instead, they theorized a new field that permeates all of space, a field that would NATURLLY Chinese letter Chinese letter Chinese letter Chinese letter itself to drive the effective theta angle to zero, effortlessly solving the fine-tuning problem. Shortly thereafter, Frank Wilczek and Steven Weinberg realized that this mechanism would necessarily produce a new, very light particle as a ripple in that field. Wilczek, with a sense of humor, named this hypothetical particle the axion, after a brand of laundry detergent because it cleaned up a messy problem in particle physics. The original axion was conceived as a solution to a deep theoretical puzzle with no initial connection to cosmology or dark matter. But once this genie was out of the bottle, cosmologists quickly realized its staggering potential. It turns out that if axions exist, they would have been produced in colossal numbers in the hot, dense conditions of the early universe. Unlike WIMP, which are heavy particles that freeze out of thermal equilibrium, axions are not thermal relics. They are born cold, or more poetically, they form a coherent wave-like condensate that permeates the cosmos. Think of it not as a gas of individual particles, but as a single, unified field oscillating throughout all of space. Because they are so incredibly light, potentially billions of times lighter than an electron, vast numbers of them are required to account for the observed density of dark matter. A single cubic centimeter of space could contain 10 trillion axions or more, a ghostly ocean of unimaginable depth flowing through everything, including you right now. Their collective behavior would perfectly mimic cold dark matter, providing the gravitational scaffolding for galaxies without the intense central cusps that plague traditional WIMP models. This dual identity, as a savior of particle physics and a perfect candidate for the universe's missing mass, is what makes the axion one of the most compelling and elegant ideas in all of modern physics. Hunting for an axion, however, is a completely different kind of challenge compared to the deep underground quest for WIMP. You cannot look for a nuclear recoil from a particle that is so fantastically light and weakly interacting. Instead, physicists use a clever trick predicted by quantum field theory, the Primakov effect. In the presence of a very strong magnetic field, an action should have a tiny probability of converting directly into a photon. The specific frequency of that photon will be directly tied to the action's mass. This has given rise to a new generation of experiments that look less like giant particle detectors and more like giant high-tech radio receivers. The most famous of these is the Action Dark Matter Experiment, or ADMX, located at the University of Washington. ADMX is essentially a super-sensitive tunable radio cavity, chilled to near absolute zero to eliminate thermal noise and placed inside a powerful superconducting magnet. The concept is breathtakingly simple in theory, but fiendishly difficult in practice. The experimenters slowly tune the resonant frequency of the cavity, scanning through millions of possible frequencies, while listening intently for an excess of microwave photons at one specific frequency. It's like trying to find one single specific radio station in a cosmic static that spans the entire dial, and the knob has to be turned with incredible precision. If a halo of actions with a specific mass is streaming through the cavity, the strong magnetic field could coax a tiny fraction of them to transform into microwaves, producing a faint but detectable signal at one unique frequency. A detection would appear as a persistent monochromatic tone rising from the quantum noise, a single pure note in the cosmic symphony, revealing the presence of the invisible ocean in which we are all immersed. The action hunt represents a beautiful convergence of disciplines where an abstract problem in theoretical particle physics provides a razor-sharp prediction for the dominant component of the cosmos. It is a testament to the interconnectedness of the universe, where the solution to a fine-tuning mystery in the quantum realm might also be the key to understanding the architecture of the cosmos on the largest scales. While WIMP detectors listen for a rare collision in the dark, action hunters are listening for a whisper of a conversion, a subtle transformation of dark matter into light. The continued silence of the WIMP searchers has only heightened the excitement around these tabletop-style experiments, which are now reaching the sensitivity needed to probe the most promising regions of action parameter space. Finding the action would be a 2-for-1 discovery of historic proportions, simultaneously nailing down the last free parameter of the standard model and illuminating the nature of the dark universe, all by listening for the faintest of songs from a particle born to solve a problem no one could have imagined would hold the key to everything. As if the cosmos hadn't already revealed enough of its eccentricities, we now turn our attention to some of its most paradoxical inhabitants, galaxies that are all framework and almost no house. Imagine finding a city that sprawls across the same vast area as New York or Tokyo, but upon closer inspection, you discover its streets are almost deserted, its skyscrapers are nearly empty, and its population is barely a fraction of what you'd expect. This is the essence of an ultra-diffuse galaxy, a ghostly metropolis of stars. The most famous of these, Dragonfly 44, located in the Coma cluster, is a perfect example. It stretches across a region of space comparable to our own Milky Way, a vast and majestic spiral. But where the Milky Way is ablaze with the light of hundreds of billions of stars, Dragonfly 44 is a dim, ethereal phantom, containing a mere 1% of that stellar population. If our galaxy is a bustling, bright metropolis, this one is a sprawling, barely lit suburb, its few stars lost in an immense volume of near emptiness. The true shock, however, came when astronomers measured its weight. By observing the motions of its star clusters and the faint glow of its nebulous light, they could calculate the total gravitational pull holding this wispy structure together. The result was staggering. To account for the high velocities of its visible components, Dragonfly 44 had to possess a colossal amount of unseen mass. Its dark matter content is overwhelming, accounting for over 99% of its total mass. This gives it a mass-to-light ratio that is off the charts, one of the highest ever recorded. For every single photon of light this galaxy emits, there is an immense, unseen gravitational anchor. It's a cosmic paradox of the highest order, a galaxy that is immense in its physical size and its dark matter content, yet it has failed spectacularly at the one thing galaxies are supposed to do: make stars. This raises a profound and puzzling question. How can a gravitational pit so deep and powerful, a potential well sculpted by a tremendous halo of dark matter, end up so barren and dim? This mystery strikes at the core of our understanding of galaxy formation. The standard story is that dark matter halos form first, and their gravity acts as a cosmic trap for ordinary gas. As this hydrogen and helium gas falls into the halo, it cools, condenses, and fragments, eventually igniting into stars. The more massive the dark matter halo, the more gas it should pull in, and the more stars it should ultimately produce. Ultra-diffuse galaxies like Dragonfly 44 completely append this tidy narrative. They possess the massive dark matter halos of a giant galaxy, yet they have the stellar content of a faint dwarf. It's as if a construction company was given the budget and the blueprint to build a skyscraper, but only ever managed to erect a few small sheds on the massive foundation. Something clearly went wrong, or more intriguingly, something fundamentally different happened during their formation. Did they start with a lack of raw material, or was the star-forming process somehow suppressed? One compelling theory places these ghostly giants in a particularly harsh cosmic environment. Dragonfly 44 doesn't float in isolation. It resides in the Coma cluster, a dense and violent metropolis of thousands of galaxies. In such a crowded environment, a galaxy can be subjected to a process known as ram pressure stripping. As a galaxy plows through the hot, thin plasma that fills the space between galaxies in a cluster, this intergalactic medium acts like a powerful wind. For a galaxy rich with cold, dense gas, the fuel for new stars, this wind can be catastrophic. It can literally blow the gas clean out of the galaxy, much like the wind stripping leaves from a tree. A galaxy that was once actively forming stars can have its fuel reservoir violently torn away, leaving it stranded, a red and dead relic that can no longer create new stellar generations. In this scenario, an ultra-diffuse galaxy could have been a more normal galaxy in its youth, but was robbed of its future by the brutal environment of the cluster, leaving its immense dark matter halo as the only testament to its former potential. Alternatively, perhaps these galaxies were always destined to be faint. Another line of thought suggests they are failed galaxies from the very beginning. In this picture, a massive dark matter halo forms just as expected, but for reasons we don't fully understand, the ordinary matter that falls into it fails to condense efficiently. Perhaps the gas was heated early on by a burst of radiation from the first stars or from a neighboring galaxy, preventing it from cooling down into the dense clouds required for star formation. Maybe the gas was simply too spread out, or the process of converting gas into stars was intrinsically inefficient. This would create a galaxy that is born old and quiescent, a cosmic stillbirth that never managed to light its fires, its vast dark matter frame standing as a silent, empty monument. Their diffuse nature makes them perfect natural laboratories because they are so dominated by dark matter and have such a sparse population of stars. The gravitational influence of the dark matter is exceptionally clean and easy to study. There is very little of the messy astrophysics like supernova explosions or spiral arm dynamics that can complicate measurements in brighter galaxies. By studying the motions of star clusters in these ethereal systems, astronomers can map the distribution of dark matter with unprecedented precision, testing whether it forms the sharp central cusps predicted by simulations or the smoother cores that observations often suggest. The existence of ultra-diffuse galaxies forces us to acknowledge that galaxy formation is not a one-size-fits-all process. the universe has more than one way to build a city of stars, and some of the resulting structures are hauntingly empty. They are the cosmic counterpoints to the dark matter-free galaxies we discussed earlier, presenting the opposite puzzle. While one class of oddballs seems to lack the invisible skeleton entirely, this other class is almost nothing but skeleton. Together, they bookend the strange and diverse ways that dark matter and ordinary matter can come together, or fail to, across the cosmos. Dragonfly 44 and its ghostly kin are not just astronomical curiosities. They are extreme case studies that probe the limits of our theories. They challenge us to understand why some gravitational seeds blossom into brilliant stellar islands, while others, just as massive, remain in the shadows, their vast potential forever locked in the dark. We have been exploring dark energy as a smooth, constant force, a simple energy density assigned to the vacuum of space. But to truly grasp why its value is so bafflingly small, we have to venture into a far more radical and mind-bending domain, the quantum nature of spacetime itself. At the heart of the cosmological constant problem lies a fundamental clash between our two most successful theories, general relativity, which describes the cosmos on the grandest scales, and quantum mechanics, which governs the wild, probabilistic world of the very small. General relativity treats space-time as a smooth, continuous stage upon which the cosmic drama plays out. But quantum mechanics suggests that at the very tiniest possible level, this stage cannot be smooth. It must be grainy, chaotic, and alive with a frantic, seething energy. Imagine zooming in on the fabric of reality, down past atoms, past nuclei, down to scales a trillion times smaller than an atom. At this ultimate frontier, known as the Planck scale, our classical intuition completely breaks down. According to quantum principles, empty space is not a true void. It is a turbulent, bubbling foam, a constantly fluctuating sea of virtual particles. Particle-antiparticle pairs spontaneously blink into and out of existence, borrowing energy from the universe for fleeting moments before vanishing. This isn't just theoretical. We see its effects in measurable phenomena like the Casimir effect. This frantic activity means that every cubic centimeter of what we call nothing should be bursting with an incredible density of vacuum energy. When we try to calculate this energy using our known laws of quantum field theory, the result is a number so colossal it would have torn the universe apart in its first instance. Yet, when we measure the actual energy density of empty space through the accelerating expansion of the cosmos, we get a value that is almost but not quite zero. The discrepancy is the largest in all of science, a factor of 1 followed by 120 zeros. This is the vacuum catastrophe, and it screams that we are missing something profound. This is where the search for a theory of quantum gravity enters the story. We need a framework that can marry the smooth geometry of Einstein's spacetime with the chaotic frenzy of the quantum world. Leading candidates like string theory and loop quantum gravity each offer a different vision of this unified reality, and both provide fascinating new ways to think about dark energy. String theory proposes that the fundamental constituents of reality are not point-like particles, but unimaginably tiny, vibrating strings. The different vibrations of these strings give rise to all the particles and forces we see. Crucially, string theory requires extra dimensions of space beyond the 3 we experience dimensions that are curled up and hidden from view. In this picture, the value of the cosmological constant, our dark energy, isn't a random input. It's the outcome of a specific way these extra dimensions are compactified. It's a number determined by the geometry of the universe's hidden folds. The challenge and the hope is that there might be a unique configuration of these dimensions that naturally yields the tiny, non-zero value we observe, effectively solving the fine-tuning problem by making our universe the only mathematically consistent possibility. Loop quantum gravity takes a different, equally radical approach. It suggests that space-time itself is not continuous, but is woven from a network of discrete, finite loops, a literal fabric of interconnected threads. At the Planck scale, this fabric is a dynamic, pixelated tapestry. In this view, the ceaseless quantum fluctuations of the vacuum don't happen against a passive, smooth background. Instead, the fluctuations are the space-time. The foaminess of space-time at this fundamental level might provide a natural cutoff, preventing the wild quantum jitters from adding up to the catastrophic energy density our naive calculations suggest. It's like replacing a perfectly smooth, and therefore infinitely divisible, surface with a digital screen made of finite pixels. There's a fundamental limit to how much energy can fit into the tiniest possible unit. The small, positive value of dark energy we measure could then be a residual effect, a kind of average leftover energy from the fundamentally discrete and quantum nature of geometry itself. So, the mystery of dark energy may ultimately be a clue pointing toward the next great revolution in physics. Its inexplicably small value is not just an accounting error, it is a beacon, illuminating our ignorance about the fundamental structure of reality. It forces us to confront the possibility that space and time are not the smooth, continuous backdrops we perceive, but are emergent properties of something deeper, more intricate, and decidedly quantum. Unlocking the secret of dark energy might therefore require more than just a new particle or field. It might demand a complete rewriting of our understanding of what space and time actually are, revealing that the force shaping the destiny of our entire cosmos is at its heart, a quantum ghost woven into the very fabric of existence. Pushing our gaze even further back in time, beyond the formation of the first mature galaxies, we approach the very threshold of cosmic dawn. This was the moment the universe finally emerged from its long, silent slumber, a period known as the Cosmic Dark Ages. For hundreds of millions of years after the Big Bang, the cosmos was a profoundly different place. It was filled with a warm, opaque fog of neutral hydrogen gas, and not a single star or galaxy existed to pierce the gloom. The universe was a vast, dark, and simple expanse, its only structure being the gentle, invisible ripples of dark matter that had been laid down during inflation. Then, somewhere in the depths of that primordial darkness, a profound transition began. The first pockets of gas trapped within the deepest gravitational wells of dark matter began to collapse. Under incredible pressure and heat, nuclear fusion ignited, and the very first stars were born. These were not the gentle, long-lived stars like our Sun. Astronomers call them population 3 stars, and they were likely behemoths, hundreds of times more massive than the Sun, burning with a ferocious blue-white intensity and living for only a few million years before dying in spectacular supernova. Their birth was the cosmic equivalent of lighting a single match in a pitch-black cathedral, but it was enough to start a chain reaction that would eventually set the entire universe ablaze. The timing and the character of this cosmic dawn, however, were not dictated by the visible gas alone. They were choreographed in the shadows by the properties of dark matter. For decades, our standard model has relied on the idea of cold dark matter, with slow-moving particles that readily clump together to form structures on all scales, from the very smallest halos to the largest galaxy clusters. This model predicts that the first stars should have formed inside these myriad tiny dark matter clumps, leading to a relatively early and gradual illumination of the cosmos. But what if dark matter isn't perfectly cold? The alternative of warm dark matter introduces a fascinating twist. If dark matter particles are lighter and faster moving, they would have possessed enough energy in the early universe to stream out of the very smallest gravitational potential wells. This streaming effect acts like a cosmic eraser, smoothing out the tiniest density fluctuations. The consequence for cosmic dawn would be profound. The formation of the very first, smallest stars would be delayed or even prevented altogether because the necessary dark matter seeds for their formation would have been wiped clean. Instead of a sky flickering to life with countless small points of light, the first illumination might have been more dramatic, occurring later in fewer, larger clumps that were massive enough to retain the warmer dark matter. This isn't just a theoretical curiosity, it's a difference we might be able to observe. The transition from a neutral to an ionized universe, driven by the intense ultraviolet light of these first stars and galaxies, left a specific imprint on the hydrogen gas that filled all of space. Neutral hydrogen emits and absorbs a faint radio signal at a characteristic wavelength of 21 centimeters. As the first sources of light began to shine, they heated the hydrogen gas and eventually ripped electrons from their atoms, a process called reionization. This altered the way the gas interacted with the cosmic microwave background, imprinting a subtle signature on the 21-centimeter signal. The pattern of this signal, how quickly it appears, how it fluctuates across the sky, and its precise structure, is a direct record of how and when the first structures lit up. A universe with cold dark matter would produce one specific pattern of 21-centimeter fluctuations, corresponding to an early, fine-grained reionization process. A universe with warm dark matter which suppresses small structures would produce a noticeably different pattern with a later and more patchy reionization history. The timing and texture of the cosmic dawn are therefore a hidden message about the fundamental nature of the dark matter particle itself. To read this ancient message, astronomers are building the most ambitious radio telescope the world has ever seen, the Square Kilometre Array. When fully operational, this colossal instrument, with its thousands of antennas spread across South Africa and Australia, will function as a single, continent-sized radio dish. Its primary mission is to map the distribution of cosmic hydrogen during the Dark Ages and the epoch of reionization with unprecedented sensitivity. It will effectively create a three-dimensional movie of the universe's first lights turning on. By analyzing the subtle ripples and shadows in this vast 21-centimeter map, scientists will be able to perform a kind of cosmic tomography. They will see not the dark matter directly, but its ghostly gravitational influence on the timing and distribution of the first luminous objects. If the map reveals that reionization started remarkably late and was driven by fewer, larger sources, it would be powerful, albeit indirect, evidence for warm dark matter. It would show that the dark sector has a slight warmth to it, fundamentally altering the initial conditions for all the structure that followed. This incredible endeavor connects the earliest moments of the universe to the technology of today in a truly breathtaking way. We are on the cusp of using a telescope built with human ingenuity to observe the end of the cosmic dark ages, an event that occurred over 13 billion years ago. The data streaming in from the Square Kilometre Array won't just show us the first stars. It will allow us to reverse engineer the properties of the invisible substance that made their formation possible. We are probing an era so ancient that it precedes every galaxy, every quasar, and every planet, seeking answers in the faint radio whispers of primordial hydrogen. The story of Cosmic Dawn is the story of how light first conquered darkness, and hidden within that story is the final, untold chapter about the true identity of the dark matter that guided the entire transformation. Perhaps the most controversial and mind-expanding attempt to solve the cosmological constant problem doesn't involve a new particle or a modification of gravity at all, but instead asks us to radically rethink the very nature of our universe's existence. This is Mystery 28, a journey into the ideas of the multiverse and the anthropic principle. The core of the puzzle is the unbelievable fine-tuning we see in dark energy. For life to be possible, for galaxies to have even had time to form, the value of the vacuum energy had to be almost exactly zero, but not perfectly zero. If it were much larger, even by a minuscule amount, the universe would have blown itself apart before the first star could ignite. If it were negative, the cosmos might have collapsed back in on itself almost immediately. The fact that we exist in a universe where this number is balanced on such a razor's edge seems like an incredible coincidence, one that defies any straightforward physical explanation. This is where the multiverse hypothesis enters the stage. What if our universe, with its specific set of physical constants and its peculiarly small amount of dark energy, is not the only one? What if it's just one bubble in an infinite, frothing cosmic foam of universes, a vast multiverse where each domain has its own unique, randomly selected laws of physics? In this grander picture, the value of the dark energy density isn't something derivable from a single, elegant equation. Instead, it's like a winning lottery ticket drawn from a cosmic hat containing every possible number, from the catastrophically large to the infinitesimally small. In the overwhelming majority of these universes, the cosmological constant is either so powerfully repulsive that no structures ever form, or so attractive that the universe instantly crunches. But in a tiny, tiny fraction of them, by pure chance, the number falls within the narrow, habitable window. And in those rare, life-friendly bubbles, beings like us can emerge to look up at the sky and wonder why the constants of nature seem so perfectly arranged for our existence. This line of reasoning is known as the anthropic principle, simply stating that the universe we observe must be compatible with the fact that we are here to observe it. It's not that the universe was designed for us, it's that we can only exist in a universe that allows for us. This idea is simultaneously profound and deeply unsettling for many scientists. On one hand, it offers a potential escape from the fine-tuning problem. There is no longer a need for a fundamental theory to predict one specific tiny number for dark energy. The theory just has to allow for a vast landscape of possibilities, and our observation simply reflects our location within that landscape. This perspective finds a natural home in certain interpretations of string theory, which suggests there could be a staggering 10 to the power of 500 or more possible vacuum states, each with a different value for the cosmological constant. Our universe would just be one data point in this inconceivably vast statistical distribution. On the other hand, critics argue that the anthropic principle is a scientific cop-out, a philosophical surrender. If we accept that a constant is the way it is simply because we happen to be here, have we explained anything at all? This approach can be seen as a conversation stopper, potentially halting the search for a deeper, more deterministic physical law that actually predicts the value we see. It shifts the goalposts from finding a cause to merely noting a selection effect. The fear is that embracing the anthropic principle could lead to a sort of scientific lethargy, where any puzzling observation is explained away by saying, well, if it weren't this way, we wouldn't be here to ask the question. It moves the discussion from the testable realm of physics into the more speculative domain of metaphysics. The debate over this is fierce and ongoing, striking at the very heart of what we mean by a scientific explanation. Proponents counter that the multiverse isn't necessarily untestable. If our universe is just one bubble in a greater metacosmos, it's possible that other bubbles could have collided with ours in the distant past, leaving an imprint on the cosmic microwave background, a kind of cosmic bruise on the sky. While no definitive evidence for this has been found, it remains a potential, albeit faint, observational signature. Furthermore, the multiverse idea makes a statistical prediction that the value we measure for dark energy should be typical of what is found in other habitable universes. It shouldn't be zero, and it shouldn't be at the very extreme edge of what permits life. It should be somewhere in the middle of the habitable range. Intriguingly, the value we have measured seems to fit this description reasonably well. It's small enough to allow galaxies to form, but large enough to be detectable and to eventually dominate the cosmos. Ultimately, the multiverse and the anthropic principle force us to confront fundamental questions about the nature of reality and our place within it. Are the laws of physics we discover absolute, necessary truths, written into the fabric of existence, Or are they merely local bylaws, the parochial rules of our own cosmic neighborhood, with entirely different physics operating just beyond the horizon of our observable universe? This mystery sits at the precarious boundary between established science and profound philosophy. Whether one sees it as a brilliant insight or a clever excuse, it represents a staggering shift in perspective. It suggests that the answer to the mystery of dark energy may not be found by looking deeper into the quantum vacuum of our own universe, but by realizing that our entire cosmos might be just one page in an infinite library of realities, each with its own story, its own laws, and its own answer to the question of why the night sky is dark and what lies in the emptiness between the stars. After decades of searching that have yielded more questions than answers, the hunt for dark matter is entering its most thrilling and decisive phase. This is no longer a niche pursuit. It has evolved into a coordinated, global scientific campaign, a three-pronged assault on the invisible universe that will leave virtually no theoretical stone unturned. The strategy is beautifully comprehensive, targeting dark matter through direct detection, indirect observation, and particle creation, ensuring that if this elusive substance is within our reach, we will find it. The next generation of experiments represents a monumental leap in scale and sensitivity, pushing the boundaries of engineering and imagination, and they carry the very real promise that a world-changing discovery could be mere years away. The first arm of this attack involves going deeper, colder, and bigger in the quest for a direct signal. The flagship of this new fleet is a project known as Darwin, an ambitious endeavor that aims to be the ultimate direct detection observatory. Imagine scaling up the liquid xenon technology of current experiments to a colossal scale. Darwin proposes a vessel containing not just a few tons, but a staggering 50 tons of ultra-pure liquid xenon, held in a state of profound stillness and cold deep beneath the Earth's surface. The sheer size of this detector is its superpower. By increasing the target mass by an order of magnitude, it dramatically increases the odds that a dark matter particle will, by chance, collide with a xenon nucleus. Furthermore, its immense volume allows for even more powerful self-shielding. Events happening near the outer edges can be discounted, while scientists focus only on the pristine, quiet signals from the deeply shielded core. Darwin's sensitivity will be so extraordinary that it will begin to probe what is known as the neutrino floor, the point where the faint, constant rain of neutrinos from the Sun and other cosmic sources becomes an unavoidable background. Finding a signal that stands out against this neutrino fog would be the smoking gun, the definitive, irrefutable proof that we have finally touched the dark matter that flows through us all. This experiment, along with other next-generation projects using different target materials like argon and crystal detectors, will create a network of ultra-sensitive ears listening for the whisper of a particle that has hidden for 13.8 billion years. Simultaneously, the second arm of the search will turn the entire sky into an even more powerful laboratory. This is the realm of indirect detection, and its new champion is the Cherenkov Telescope Array, or CTA. While current telescopes like Fermi have scanned the skies for gamma rays, the CTA represents a quantum leap in capability. It won't be a single telescope, but a vast array of over 100 telescopes spread across 2 sites in the Canary Islands and Chile, designed to capture the fleeting flashes of Cherenkov light produced when high-energy gamma rays strike our atmosphere. The CTA will be the most sensitive instrument ever built for viewing the universe in very high-energy gamma rays, and this newfound vision is crucial for the dark matter hunt. Its primary targets will be the same as before: dwarf spheroidal galaxies and the galactic center, but with a resolution and sensitivity that will finally settle long-standing debates. The CTA will be able to scrutinize the faint gamma-ray excess at the heart of our galaxy with such precision that it can distinguish between a smooth, dark matter annihilation signal and the clumpy, point-like glow of a population of pulsars. It will also search for the telltale lines in the gamma-ray spectrum, a sharp, monoenergetic spike that would be the unmistakable fingerprint of dark matter particles annihilating into pure light. By looking at the universe with this new, incredibly powerful eye, we are not just hoping to see a signal, we are building a machine capable of ruling out vast swaths of theoretical models, forcing the dark sector out of hiding. The third and most confrontational approach is to forget about searching for dark matter in the wild and instead to create it ourselves. This is the domain of high-energy particle colliders, and the planned Future Circular Collider, or FCC, is poised to take this to the next level. If dark matter particles are indeed part of a hidden sector that connects to our own through feeble forces, then slamming ordinary particles together with unprecedented energy could be the key to knocking them into existence. The FCC, a proposed collider with a circumference of over 90 kilometers, would dwarf the Large Hadron Collider. It would smash protons together at energies far beyond what we can achieve today, essentially recreating the conditions of the universe a fraction of a second after the Big Bang. In these fiery collisions, anything that is permitted by the laws of physics can and will be produced. The strategy here is not to see the dark matter particle itself. It would fly right through the detectors without a trace, but to spot its absence. Physicists would look for collisions where the total momentum of the detected particles is unbalanced, indicating that something invisible and undetectable carried away energy and momentum. This missing energy signature would be a powerful hint that we have, for a fleeting instant, created a particle from the dark sector. The FCC, along with other precision experiments, would act as a cosmic forge, actively producing the very substance we are trying to find and studying its properties in a controlled environment. What makes this moment in science so electrifying is the collaborative and complementary nature of this global effort. It is no longer a competition between different techniques, but a unified strategy. A signal seen in one arena would immediately guide the others. A hint of a specific particle mass from the LHC or FCC would tell the Darwin collaboration exactly where to focus their search. A peculiar gamma-ray line spotted by the CTA would give collider physicists a specific energy to target. This multi-front war on ignorance is a testament to human curiosity and determination. We are throwing everything we have at the problem, from the profound quiet of deep underground laboratories to the violent, energetic collisions in particle accelerators and the grand, sweeping surveys of the night sky. The possibility that one of these experiments within the next decade or two could crack the mystery wide open is not just hopeful thinking. It is a very real prospect based on the breathtaking capabilities of the tools we are now building. The discovery of dark matter would be more than just a Nobel Prize-winning moment. It would be a fundamental milestone for humanity, a profound shift in our cosmic self-awareness, revealing the true nature of the invisible universe that has been the silent architect of our entire existence. And so we arrive at the final and perhaps most profound mystery of all. After this grand tour of ghostly matter and repulsive energy, of cosmic scaffolding and impossible galaxies, we are forced to confront a possibility that is as humbling as it is electrifying. What if we are completely wrong? What if our entire framework, the lambda cold dark matter model that has been the bedrock of cosmology for decades, is fundamentally flawed? This isn't just a question of tweaking a parameter or discovering a new particle. It's a challenge to the very narrative we have woven to explain the cosmos. The tensions we've discussed are no longer mere anomalies. They are accumulating cracks in a once unshakable foundation. The Hubble tension reveals a stubborn disagreement about how fast the universe is expanding. The S8 tension suggests the cosmos is smoother than our model predicts. The planes of satellite galaxies and the existence of galaxies with far too much or far too little dark matter all point to physics that our standard playbook doesn't contain. When so many pieces of the puzzle refuse to fit at some point, you have to wonder if you're trying to solve the right puzzle at all. This crisis of confidence has propelled physicists to consider alternatives that go far beyond simply modifying gravity like men. One of the most intriguing is the concept of emergent gravity proposed by the theoretical physicist Eric Verland. This idea turns our understanding of reality on its head. We're accustomed to thinking of gravity as a fundamental force, one of the basic ingredients of the universe. But what if gravity isn't fundamental at all? Emergent gravity suggests that what we perceive as gravity is actually a side effect, a collective phenomenon that emerges from the interactions of countless microscopic degrees of freedom in spacetime, much like the concept of temperature emerges from the jostling of countless molecules. In this view, dark matter isn't a substance, it's an illusion. The extra gravitational pull we attribute to invisible matter is actually a consequence of dark energy itself. As dark energy accelerates the expansion of the universe, it imbues empty space with a kind of elastic resistance. When ordinary matter is present, it disrupts this elastic medium, and the way the medium responds to this disruption creates an additional gravitational effect that mimics the presence of dark matter. It's a breathtakingly elegant idea. Dark matter and dark energy, the two great mysteries, are unified into a single, deeper phenomenon. While emergent gravity is still in its infancy and struggles to explain all observations like the bullet cluster, it represents a paradigm shift, urging us to think not in terms of new particles, but in terms of the very nature of space, time, and information. Then there are theories that venture into realms that sound like pure science fiction, proposing that our entire three-dimensional universe is just a membrane or a brain, floating within a higher dimensional space called the bulk. In these brain world scenarios, the forces and particles we know are trapped on our three-dimensional brain, but gravity, because it is linked to the fabric of spacetime itself, can leak out into the extra dimensions. This leakage could explain why gravity is so weak compared to the other forces. More relevantly, it could provide a radical new explanation for dark matter. What if the dark matter halos surrounding galaxies aren't made of particles on our brain at all, but are actually the gravitational influence of other parallel brains hovering nearby in the higher dimensional bulk? From our limited three-dimensional perspective, we would feel the gravity of these unseen worlds and interpret it as a mysterious, invisible substance within our own universe. Dark energy in this picture could be the gentle pressure of the bulk itself, pushing our brain and causing the expansion of space to accelerate. These ideas push the boundaries of testability, but they demonstrate the lengths to which theorists are now going, envisioning a cosmos of unimaginable depth to solve the puzzles in our own. Facing these radical alternatives, it's tempting to feel that cosmology is in a state of disarray. But the exact opposite is true. This moment of profound uncertainty is not a sign of failure. It is the unmistakable sound of a scientific revolution in the making. The history of science is written not in the steady accumulation of facts, but in the violent overturning of established ideas. We once believed the Earth was the center of the universe, then we believed the Sun was, and then we believed our Milky Way was the entirety of creation. Each time, a crisis of anomalies forced a grander, more humbling, and more accurate view of reality. The lambda cold dark matter model has been phenomenally successful, but its growing list of tensions is a gift. It is the universe speaking to us, telling us that we are on the verge of something much bigger. The true progress of science happens not when all the answers are clear, but when the most fundamental questions are up for grabs. We are standing at that precious and thrilling frontier. The greatest mystery of dark matter and dark energy, therefore, is not what they are, but what their ultimate discovery will force us to become. It will compel us to see the cosmos with new eyes, to rewrite the textbooks, and to embrace a reality that is, as it has always been, far stranger and more wonderful than we ever imagined. And so, our journey through the shadows of the cosmos comes to a close for now. we have ventured from the silent, ghostly pull that dictates the spin of every galaxy to the repulsive phantom energy scripting the universe's ultimate fate. We've stood as cosmic detectives before the evidence of bullet clusters and the paradox of galaxies with no dark matter, wrestled with the maddening silence of underground detectors and the faint, tantalizing whispers from the galactic center. We have charted the great tensions in our maps, the universe expanding just a little too fast and looking a little too smooth, and dared to consider that the answer might not be a new particle, but a rewriting of gravity itself or a glimpse into a hidden multiverse. These 30 mysteries are not merely items on a list. They are the bleeding edge of human understanding, the places where our most cherished models strain and crack under the weight of new evidence, revealing just how much we have yet to learn. This grand puzzle of dark matter and dark energy is far more than an academic exercise. It is a fundamental quest to understand what the universe is truly made of, to read the hidden blueprints of reality. For all our brilliance in comprehending the life cycle of stars and the nature of the atoms that make us, we are forced to confront the humbling truth that over 95% of the cosmos is completely unknown to us. This isn't a small gap in our knowledge. It is the central challenge of 21st century physics, a challenge that calls into question the very foundations of our science. The lambda cold dark matter model has been a magnificent guide, but the mounting anomalies are a clear signal that we are on the verge of something far grander, a revolution in waiting that will likely shatter our current paradigms and unveil a universe stranger than we can currently imagine. That inevitable revolution, however, depends on a continuous chain of curiosity reaching from today into the future. The answers to these profound questions will not come from our current tools alone, but from the next generation of great observatories from telescopes like the Vera Rubin and Nancy Grace Roman that will map the sky in unprecedented detail, and from the brilliant young minds who will look at the same data we have and see something entirely new. They will be the ones to finally hear the clear signal in the noise, to devise the elegant experiment that captures the elusive particle, or to conceive the revolutionary theory that unites the quantum and the cosmic. The greatest discoveries in this field are still ahead of us, waiting in the dark for the light of a new idea to fall upon them. So, as we look up at the star-filled night, let's remember that its beauty is only a tiny fraction of the story. The true cosmic drama is playing out in the vast, invisible realms of dark matter and dark energy, and each of us has a front-row seat to this unfolding epic. Keep looking up, keep asking questions, and keep that sense of wonder alive. The universe's deepest secrets are not locked away forever. They are simply waiting for the right moment and the right mind to be revealed. We want to know which of these 30 mysteries captivates your imagination the most. Was it the terrifying possibility of a big rip, the ghostly evidence of the bullet cluster, or the bizarre existence of galaxies without dark matter? Let us know in the comments below, and if you're eager to continue exploring the wonders of the cosmos, be sure to subscribe for more journeys to the